As a reminder, we are asking you to please rename yourself so that your first and last name shows up. All questions today will be posted through the slido.com website or Slido app, and the code is SEAS 2024. I believe we're about ready to get started. We want to remind you, if you have entered and you do not have your first and last name on your image, please include that now so that we know each team member is here. And also, all questions will be posed through the slido.com website or app, and the code is SEAS 2024. Welcome to the continuation of the 2024 NASA STEM Enhancement in Earth and Space Science High School Interns program. SEAS is a collaboration between NASA and the University of Texas at Austin's Center for Space Research. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and space contractors, and been hired by NASA working on missions such as Cassini, Europa, and even managing the launches at Kennedy Space Center. In 2024, we received over 3,000 applications. 1,861 of those were completed, and we selected 108 11th grade students on site and 125 virtual students as participants who were assigned to 23 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science modules, Python coding, and project-specific work before starting their own project. Interns heard from 10 NASA subject matter experts that highlighted NASA missions, opportunities, and careers during the course of this internship as part of the NASA SEAS Speaker Series. You are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller, Laura Tomlin, and myself, Margaret Baggio, the managers of the SEAS program, and our communications coordinator, Angelica Gruzinga, we want to say welcome to NASA SEAS 2024. Today, we will have 25 teams and individual project video presentations. We will divide it into 3 sessions with 2 20-minute breaks throughout the day. Project video presentations will either be 5, 10, 15, or 20 minutes in length, followed by a 5-minute Q&A. Please post your questions on the slido.com website or app and use the code SEAS 2024. But first, we will divide the day's presentations into 3 sessions. Here's session 1, session 2, and session 3. We will have presentations by teams followed by the 5-minute Q&A. We'll invite each team presenting to turn on their cameras and their mics to answer the questions posed by those listening at the end of their video. During the 20-minute break, we invite you to watch the video highlights of the student intern produced products as part of the Earth and Space Science and Python coding projects. Our first presentation is from the In-Space Refueling team, all about the bubbles. The mentor for this team is Dr. Kevin Crosby, who teaches physics and astronomy and computer science at Carthage College and serves as the director of Wisconsin Space Grant and manages the Carthage Space Science Program. The project assistant for this group was Mauro Esquivel. Please join me in welcoming the Refueling and Space team with their project analysis of refueling architectures for Artemis 3 through 5 human landing system providers.
Hello, we are Replio, short for Refueling Endeavor for Prolonged Lunar Exploration and Operation. Our project analyzes the refueling architectures of Artemis 3 and 5 human landing system providers with the help of our mentor, Dr. Kevin Crosby.
Hello, I'm Angel Guerra and I'm from Mission, Texas.
Hi, my name is Rithickson Walker and I'm from Frisco, Texas.
Hello, my name is Atul Anand from Bridgewater, New Jersey.
Hi, I'm Varian Johnson and I'm from New York City, New York.
My name is Noya Vainbrandt and I'm from Austin, Texas.
Hello, my name is Yair Villarreal and I'm from Raleigh, North Carolina.
Hi, my name is Enrique Perez de Leon and I'm from Dallas, Texas.
My name is Caleb Berumen, I'm from El Paso, Texas, and thank you to Dr. Crosby and Model for their support through the project. We'll begin with describing Artemis and Gateway. Athul?
Artemis's goal is to establish long-term presence on the moon, allowing us to achieve specific scientific goals, including collecting rock samples and analyzing water ice on the lunar surface. NASA has decided to outsource the design and construction of the Human Landing System, or HLS for short, a crucial component of Artemis, to private companies. SpaceX was awarded a contract for their Starship HLS for Artemis 3 and 4. Blue Origin's Blue Moon HLS will fly on Artemis 5.
The Lunar Gateway, another component of the Artemis program, is a space station that will be stationed in near rectilinear halo orbit to provide constant communication with the Earth and Moon. Trips to the lunar surface will also be cheaper and more sustainable with Gateway. Modules that constitute the Lunar Gateway will be delivered from ESA, NASA, JAXA, and the CSA. One of these modules is the Power and Propulsion Element, or PPE, which will contain the engines and refueling capacity for Gateway. Gateway will also have antennas that are capable of relaying high and low frequency X and Ka bands to all lunar rovers, landers, and satellites.
This image shows the concept of operations for Artemis 3. Stage 1 on the left is the launch of Starship HLS to low Earth orbit, or LEO for short, via the Super Heavy booster. Then propellant tanks refuel the propellant depot in LEO, from which Starship HLS refuels in LEO. Shortly after, Starship HLS enters NRHO and docks with Orion. Starship descends to low lunar orbit, or LLO, before landing on the moon. After living on the moon for about a week, the two astronauts on the lunar surface will return to Starship and rendezvous with Orion in NRHO. Once the two astronauts disembark from Starship and reboard Orion, Orion will perform an orbit departure burn. Orion will perform one more entry burn before entering Earth's atmosphere. Starship HLS will return to LEO and then descend to Earth along with Orion to be reused in future missions. The initial operation of Artemis 5 uses Blue Origin's New Glenn rocket to launch Lockheed Martin's cislunar transporter into LEO. The transporter is launched in two parts, a tug and a tanker. The tanker refuels the tug, and then the two parts dock and launch into NRHO. In NRHO, the Blue Moon crew lander will dock with the transporter. The transporter will then refuel Blue Moon. Blue Moon combines with Gateway and awaits Orion. Once the crew transfers to the Blue Moon HLS, it will transfer to LLO and to leave the lunar surface. Upon leaving the moon, some of the Blue Moon HLS gets left behind with the descent stage, and the rest of the spacecraft goes back to Gateway. At Gateway, the crew will re-dock Orion and come back to Earth. Blue Moon, HLS, and the Cislunar Transporter will also come back to Earth and be reusable for future missions.
The goal of the first half of our project was to conduct a comparative analysis of 4 possible orbital trajectories for the Artemis missions to the Moon. Our goal was to find trajectories that allowed the HLS rockets to get from LEO to the Moon and back with a propellant margin of 10%. This means that there is a 10% of propellant to provide a window for error for gauging the amount of propellant available, as required by NASA, because we just do not have the reliable means of gauging propellant accurately. We also varied cargo masses for each HLS to test how cargo mass affects propellant margin. Since both Blue Moon and Starship are supposed to carry up to 20,000 kilograms of cargo mass, we tested 10 different cargo masses in 2,000 kilogram intervals.
We conducted our research using our mentor's Python code, which we altered. The code already included the delta V and transit time for trajectories based on the delta V map of the solar system created using the rocket equation. We added ballistic transfer, the ability to refuel an NRHO, and the ascent stage option for Blue Moon. We inputted the HLS spacecraft-specific information seen in the middle left picture. We then mapped out our trajectory with the menu seen on the bottom left picture. The code produced a table including transit time, a graph of propellant consumption over time, and an assessment of mission success or failure.
This is a table of the different parameters we inputted for each of the HLS spacecraft. As you can see, Blue Moon is smaller but is supposed to have the same cargo carrying capabilities as the more powerful Starship. Additionally, not much information is available on Blue Moon, so we could not find the exact mass left behind on the lunar surface, so we assume this to be around 90% based on the Apollo missions.
All trajectories to the Moon require transfers between orbits. Each transfer necessitates a certain amount of delta V or change of velocity to complete the maneuver. In order to visualize the delta V requirements for the several possible trajectories NASA may take on the Artemis missions, I create a map. Starting from LEO on the left side of the slide, the 4 transfer orbits, TLI to NRHO, DRO, ballistic, and TLI are labeled in blue, orange, red, and purple respectively. Each orbit places the capsule on the Moon, returns them to LEO via TLI, and these orbits will be expanded upon in the following slides. For the TLI to NRHO transfer, NASA plans to send the desired spacecraft to the Moon via TLI or translunar injection into an orbit around the Moon and near rectilinear halo orbit, or NRHO. NRHO is a highly elliptical near-polar orbit around the Moon which uses the gravity well at Lagrange point 2 to stabilize itself and is at an inclination just below 90 degrees. Once NRHO, the spacecraft will then descend to low lunar orbit, or LLO, in preparation for a final descent to the Moon. The spacecraft will then retrace its steps by returning to LLO, NRHO, and finally a return to TLI to ELEO. If the Blue Moon HLS were to take trajectory 1, the mission would only be successful meaning the 10% propellant margin if the craft took no cargo to the Moon. Any mass added by cargo would cause the propellant margin to fall below 10%. This is largely due to the weak thrusters used to propel the craft, meaning that any kilogram of weight added burns more propellant than that of a more powerful craft. In stark contrast to Blue Moon, Starship never succeeds using this trajectory. However, the impact of cargo mass on the propellant efficiency of the craft is far less severe, with the propellant margin decreasing by about 0.06% per 2,000 kilograms. This trajectory should be avoided by Starship.
The second trajectory starts from low Earth orbit and takes a low-energy ballistic lunar transfer, or BLT, to NRHO, which saves delta V and has a relatively long transit time in comparison to a traditional translunar injection, which uses a high-energy direct transfer. The BLT uses the gravitational pull of the Sun to raise the apogee, or the highest point in the orbit, past the orbit of the Moon. It then performs a lunar flyby, where the craft inserts itself into NRHO. From there, the craft lowers its orbit into a global low lunar orbit, or GLLO. The craft then lands on the lunar surface. The craft then returns to NRHO via GLLO, from where the crew transfers to Orion at NRHO. From there, the HLS landing system transfers back to low Earth orbit, from where it can return to the Earth to be reused. For trajectory 2, Blue Moon fails the mission for every cargo mass tested, as the projected propellant margin after the mission is under the NASA requirement of 10%. The mission is still possible until the cargo mass reaches just under 12,000 kilograms because the propellant margin is greater than 0%. However, above that cargo mass threshold, the propellant margin becomes negative, meaning the mission fails due to a complete lack of propellant. If Starship takes trajectory 2, it passes the mission for every cargo mass, as the propellant margin is well above the NASA requirement of 10%. While the mission saves a fair amount of propellant, the amount saved depends on factors including maneuver execution error and navigation accuracy. Overall, this trajectory presents the best option for Starship HLS, despite its added transit time and complexity.
This is the third trajectory. Instead of a TLI directly to NRHO, the HLS systems would enter a distant retrograde orbit, or DRO, an orbit that relies on the Earth-Moon Lagrange points L1 and L2. We did this to see if such a trajectory could decrease transit time. TLI was not included in the trajectory description because in our code, a TLI was already included in the LEO to DRO transfer. Once the HLS enters NRHO, the rest of the trajectory stays true to the pre-existing Artemis trajectory plans. Trajectory 3 successfully closed the mission for Blue Moon, although the mission failed when the cargo mass was added. The Blue Moon rocket could reach LEO successfully with up to 12,000 kilograms of cargo, but the propellant margins with cargo was added are smaller than 10% and therefore do not meet NASA requirements. This mission fails for Starship for all cargo masses due to the 10% PM requirement. Only with an accurate propellant gauging technology could the mission succeed for all cargo masses tested with a lower propellant margin requirement.
Trajectory 4 is the final proposed trajectory and takes a unique approach. In other trajectories, stopping and refueling at NRHO are deemed necessary both to and back from the Moon. However, in Trajectory 4, Blue Moon and Starship skip both designated stops to save fuel and time, instead of going from LEO directly to global LLO and bypassing NRHO. Unfortunately, this idea of skipping NRHO proved to be ineffectual. Out of all of the trajectories for Blue Moon, Trajectory 4 is the only trajectory to fail without cargo by more than half a percentage and the only trajectory to result in a negative percentage for every cargo mass. Not only does this fail to meet NASA requirements, but the drastic negative percentages signify that this trajectory is impossible to complete, even if we ignore the 10% propellant margin. This same effect can be observed on Starship as well. Although this trajectory proved impossible, it further emphasizes the importance of NRHO for any trajectory or mission to the Moon, as without it, spacecraft cannot reach the Moon.
The left-hand graph records the transit time in days for each trajectory. Since both options don't carry humans for trajectories 1 through 3, the transit time to NRHO is irrelevant, since humans aren't on board. The right-hand graph shows the transit time for each trajectory with humans. Trajectories 1 through 3 have the same transit time with humans since they're only going from NRHO to the lunar surface. However, in Trajectory 4, the transit time is 3 days longer with humans on board than for other trajectories, since it skips the docking with Orion in NRHO and instead takes a high-energy fast transfer to global low lunar orbit and the lunar surface. If cargo and humans had to be delivered to NRHO or the lunar surface quickly, Trajectory 3 would be the best, as it minimizes human time on board the HLS and has the least total transit time.
In conclusion, due to the complexity of the Artemis missions, it is crucial to find a balance between efficient propellant usage, cargo mass, and transit time. For Blue Moon, this was achieved in trajectories 1 and 3, with both orbits achieving the necessary propellant margins with relatively short transit times. However, this comes at the cost of limited cargo carrying capability, an issue that should be addressed by Blue Origin. By contrast, Starship has a high cargo carrying capability and only suffers due to its low propellant margins, with the exception of Trajectory 2. NRHO refueling is a simple fix to this, and without it, any viable trajectory taken by Starship may result in a one-way trip to the Moon.
We also looked at refueling the Lunar Gateway, inspired by our mentor Dr. Crosby's research. Due to the unusual behavior of liquids in microgravity, refueling architecture is more complex in space.
Propellant has been a major limiting factor of payload capacity for launch systems due to the large amount of space and weight that propellant tanks consume, making in-space refueling essential. On Gateway, the PPE relies on xenon for its engines. These will be used for attitude control and must be refueled about twice in its lifetime. The vessel in which the xenon is stored can be observed through this diagram. Xenon is refueled through the xenon transfer system, which utilizes a pressure differential to refill tanks, a process known as blowdown. However, problems arise when gas bubbles move into the receiving tank during propellant transfer.
There are challenges posed by refueling in microgravity as opposed to Earth's gravity. In a microgravity environment, the force of adhesion dominates, meaning that the propellant will cling to the walls of the tank rather than settling at the bottom. This creates a bubble at the center of the tank, called an ullage, only allowing the tank to be partially filled. This phenomenon occurs in the xenon tank on the PPE, meaning a better architecture should be found to minimize ullage formation. This video models the distribution of propellant in a fuel tank in microgravity. Red areas represent fast-moving fluid, while blue areas are slower moving. As the liquid settles, it sticks to the walls of the tank due to capillary action.
To separate pressure and gas from liquid propellant and ensure that only liquid flows out of the tank outlet, propellant management devices, or PMDs, are used. One example of a PMD used in the tank designs for the PPE is a vane, as seen in the bottom left image. Vanes are thin metal plates along the edges of a tank that are shaped to take advantage of adhesive capillary forces, which cause the propellant to crawl along these plates and collect in the angles between the plates and the tank walls. This PMD is cost-effective and lightweight, but does not target ullage formation directly, preventing them from being used standalone. Sponges, which can be seen in the right two images, are similar to vanes, but their position in the tank is different. They are perforated contoured metal sheets in a circular pattern around the tank outlets to control propellant movement. However, sponges are quite heavy. Although sponges that use perforation are lighter, they're often less efficient at controlling propellant movement. Like vanes, they consist of no enclosures, but they are more densely structured.
Bladder and diaphragm designs are another option for a refuelable tank. A bladder tank, as seen on the left, consists of an inflatable container housed in a rigid, pressurized cell. As propellant flows into the bladder, pressurant is vented from the shell to maintain a constant pressure in the tank. A diaphragm, shown by the diagram on the right, keeps the propellant and pressurant in separate hemispheres. As the propellant is refueled, the diaphragm is pushed into the pressurant hemisphere, and as it empties, the diaphragm is pushed back. This allows for a constant pressure to be maintained and for accurate gauging of the propellant remaining based on where the diaphragm is. A solution we propose is to maximize surface area within the tank to increase the amount of propellant that can be captured by capillary action. At the same time, this slows the progression of propellant towards the pressurant valve, allowing more pressurant to be vented before the propellant reaches the valve. Our design consists of a honeycomb-type structure throughout the tank as shown in the diagram. In tubes of small enough diameters, liquid behaves similarly in gravity and microgravity environments, meaning an ullage doesn't form. This is supported by the fact that there seems to be little increased risk of gas bubbles forming in blood vessels in microgravity. Based on this, the walls of the honeycomb should be a maximum of 1 centimeter apart. The main disadvantage is that the honeycomb structure could add significant mass to the tank. Because of this, a material used for the structure should be the thinnest and lightest possible material that is still structurally rigid, non-porous, and non-reactive. We propose the aluminum alloy 6063 for this purpose, given that it is light, weldable, unreactive, and high in tensile strength.
Another group of PMDs are screen channel liquid acquisition devices, which utilize direct flow paths from the source to the tank outlet to facilitate the flow of propellant. This type of PMD can be divided into two main categories: start baskets and total communication devices. Start baskets are small modules that surround tank outlets to hold propellant near the tank outlet. Total communication devices allow for propellant management across the entire flight time. They consist of a network of channels along the tank walls. The channels have one side with a porous barrier and two sides with solid metal plates. The porous barrier allows propellant to enter the channel but blocks large gas bubbles. A pressure differential between the outside and the inside of the channels pushes the propellant through the barrier. Screen channel LADs are a very customizable PMD, as the geometry of the channels and the type of porous barrier used can be changed to meet mission needs. Lightweight materials can be used for the channel structure to minimize the weight of this PMD.
Due to the extensive process involving the designing components for Gateway, NASA is reluctant to change the current tank design, which is difficult to refuel. However, for future refuelable missions, other tank designs should be considered, such as the ones outlined in our presentation. Additionally, NASA should consider a wider range of PMDs and use them in conjunction in order to maximize propellant management and prevent ullage formation. Although vanes and sponges are used by PPE on Gateway, NASA should invest more time in researching more complex PMDs like screen channel LEDs in order to maximize efficiency during refueling.
SEAS had many highlights. Challenging yet rewarding work pushed us to our limits, but we always had our amazing and knowledgeable mentor, Dr. Crosby, and each other to rely on. Each activity brought us so much fun, but more importantly, brought our team closer together. The workload led to the challenge of overwhelming sleepiness, but on the whole, our experiences have been extremely positive, and the benefits are definitely worth sacrificing a few hours of sleep.
My favorite part throughout SEAS has been our lectures that are filled with innovative ideas about real-world science applications.
I am very grateful for the opportunities that SEAS has provided me. I now know for sure that I want to go into the aerospace industry, and I have made some lifelong connections.
SEAS has provided me with a fantastic opportunity to get acquainted with the rigors of being an aerospace engineer and allow me to meet phenomenal, like-minded people I would have never met without this program.
Seas will forever hold significance to me as it held long working nights with the brilliant minds beside me and collaborative meetings to solve complications.
I'm thankful for the opportunities SEAS has provided. Since I'm from North Carolina, major opportunities like a Johnson Space Center tour or a mentor like Dr. Crosby isn't easily accessible.
SEAS has made me eager about what's to come for space exploration, and I feel even more confident in venturing even further into the world of STEM.
I feel so lucky to have had the opportunity to come to SEAS this summer. I've become so invested in the fascinating research I've been able to do that it doesn't even feel like work.
My favorite part was with my mentor and team. They were some wonderful, amazing, and smart people whom I had an amazing experience with. With a special thanks to Margaret Baggio and Selena Miller, along with Laura Tomlin and the rest of the SEAS staff, this experience has been life-changing, and we have all grown as students, engineers, and researchers.
So we invite all of the in-space refueling team to please turn on their cameras and unmute their mics. We have several questions for you. Can you please explain again the process you used for fuel tank design?
Yeah, I can take that question. So we were first inspired by our mentor, Dr. Crosby's research, which is on moving the ullage in the fuel tank around. And that can be quite difficult to do in the current tank designs that are being used. But there are other tank designs available, which we decided to look into because if the tank had been designed to minimize the ullage formation to start with, we wouldn't have the current problems that we're seeing. So we looked into previous tank designs that have been used, and then we decided which would be most suitable for refueling xenon on the power and propulsion element.
The next question is, would you please explain what are Lagrange points and why are they important for your project?
I can take this one. A Lagrange point is essentially a point in space in which the gravitational forces of three bodies tend to sort of balance out. You can think of it like a parking spot in space. So they have very highly stabilizing properties, and they're important in this project because near rectilinear halo orbit utilizes the Earth-Moon Lagrange point 2 to sort of stabilize itself. Because if it was just a low lunar orbit, it would be the orbit itself would be more susceptible to the perturbations or gravitational forces of additional objects like the moon or other planets or even the sun itself. So
Great. So the comment was well done. It seems like this was a really high-level learning curve. What were your biggest challenges with this research?
Yeah, I can take this question. So I think our biggest challenge was we had to rely solely on publicly available data, and that was especially hard to do when finding the delta V's required for the different trajectories, as well as for analyzing the Artemis architecture, specifically Artemis 5, because of a lot of the data is still private to the companies, and so that was a huge challenge trying to rely only on that public data.
The next question is, why is xenon preferred fuel over the possible fuels available?
I can take this question. So the power and propulsion element uses something called a solar electric ion propulsion engine, which means that it ionizes the xenon gas and then uses the charged ions to create momentum. And xenon is ideal because it's a noble gas, so it's non-reactive, and that makes it easier to store and easier to work with in general.
Next question. This is a really complex project. How much knowledge about fuel usage did you have before coming to SEAS, and how did you divide up the task and workload?
I can answer this one. I can't turn my camera on for some reason, but we did not have a ton of prior knowledge. We got a lot of reading from our mentor, Dr. Crosby, and so a lot of our prior knowledge came from that. And then we basically just kind of divided up into three teams, one doing literature reviews and just getting more background information, a team also that focused on the trajectory aspect of our project, and then our last team focused on the refueling aspect of our project.
How does the process of determining orbital trajectory compare to NASA's process?
I could take this one. I can't turn on my camera either for whatever reason, but basically, the processes are actually pretty similar. However, while NASA has access to supercomputers and much more powerful computing resources than us, we only have access to Python code, simple Python code to calculate our trajectories. And the way we found out these trajectories was mainly research and help from our mentor, Kevin Crosby.
And the question is, what is the PMD most often used by NASA? How does your design maximize propellant usage compared to the standard?
Yeah, I can take this question. So the PMD most often used by NASA that is being used on the power and propulsion element are vanes and sponges, which we talked about are very lightweight in design and are very flexible in terms of what materials can be used. But in terms of the second half of the question, our design, specifically the honeycomb design, it essentially the hexagonal tubes take advantage of the capillary action that is facilitated by the interior angles of the hexagon. And so by doing that, we are allowed to allow the propellant to flow through the tubes more easily and facilitate that flow because the propellant can collect along those different interior angles. And so that's how our design can be more efficient.
Excellent. Y'all did an excellent job with your research. And I know that we all learned a lot from your presentation. So we will continue with team presentations from the Earth System Explorer team. Mentors are Dr. Rusty Lowe, Cassie Sofing, Andrew Clark, all with the Institute for Global Environmental Strategies, Peter Nelson with Globe Land Cover, and Dr. Erica Podest in JPL's Earth Science Division. The Earth System Explorers project had the largest number of student interns, with 47 students completing projects. We will review 3 teams with their research and then open it up for questions and answers. Please welcome the Earth System Explorer team, highlighting their research on using image classification and object detection to identify trees and power lines. Team.
Our project was using image classification and object detection to identify trees and power lines.
I'm Zara Callahan.
I'm Philip Cow.
I'm Andrew Carson.
And I'm Kevin Akua.
For some background information, electricity is crucial for us to live our lives. Without it, we can't communicate, store food, or get information. Because of recent events such as Hurricane Beryl, our team tackled the issue of natural disaster preparation. As you can see on the right, Hurricane Beryl made a significant impact on Houston and the surrounding area.
Our goal was to identify trees and power lines in the same image so we can reduce power outages and storms. We created an AI model using citizen science to classify images and make sure that the human touch got the images classified correctly. And the AI model will be able to identify images that have trees and power lines in the same picture. Our dataset included 1,103 photos taken as up photos from the Globe Observer app. It included 47 areas of interest, which are shown on the bottom left. 37 up photos were included in each area of interest, which are shown in the middle, and they included data points, which are shown on the bottom right.
So the platforms we used was Globe Observer, which is a citizen science app that lets volunteers to take directional images. Also, it allows them to take images up and down, and we focused on the up images. Next, we used ChatGPT to generate the code used to process the data, and Google Colab as the platform to run the Python code to process and convert all the data. Next, we use Zooniverse, which is another citizen science platform that allows volunteers to label and annotate images. Lastly, we use RoboFlow, which is a website that provides code to train and test a YOLO object detection model after annotated images are uploaded. So for data processing, we started off with exporting the URL of all the up images using the Globe Advanced Data Access tool, using a script to open each of the images in a Google Drive folder. Then we created a Zooniverse project with all the images and exported the gathered annotated data using a CSV file. Then we generated code to extract and average the coordinates of all the bounding boxes drawn around the power lines and tree canopy, and generated code to convert those JSON formatted boxes into coco.json files, which is a format that could be read by RoboFlow in the object detection model. Additionally, a manifest was included with each image that includes metadata like latitude, longitude, and the elevation where the image was taken. So Zooniverse in a bit more detail, the annotations look like the images on the left where volunteers are asked questions. Additionally, multiple people could classify the same image, which made sure we had to filter by majority. So the code was generated automatically to move images from our image folder to our filtered image folder based on the response to the first question.
Due to time constraints, we were unable to run the full classified dataset by the time of the symposium. However, we were able to export a test dataset and confirm that Zooniverse classifications and annotations are able to be exported and extracted as CocoJSON formatted files. This can then be used to train a YOLO object detection model, and once we're able to train a model based on the full dataset, we'll be able to test the accuracy.
For future work, we believe that there are certain aspects of our project that could be further improved, such as training the model with a larger data set from data gathered from different years, and not just 2024, which will help improve the accuracy and variety. Launching an official Xenoverse project to attract more volunteers would help speed up the rate of image classification, and overlaying the training data on a map, which would allow us to identify areas more at risk. This project could help us to know ahead of time what areas are most likely to lose power during heavy storms by finding power lines near trees, which can fall and damage the power line cables. As a team, we've agreed that the highlights of this internship was using the Globe Observer app to collect land cover data, as it gives you firsthand experience of data collection, working in teams to come up with and execute research, and learning about the research done by other scientists and experts in weekly meetings, as it gives you more insight on future topics.
So NASA STEM was my first exposure to AI and allowed me to learn how data is processed, transformed, sorted, and analyzed, and also introduced me to citizen science platforms like Zooniverse and Globe Observer, which I'll probably use in the future to collect data.
Thanks to NASA STEM, I've been able to explore and experience the process of scientific research, along with how impactful it can be to future researchers and scientists.
Through NASA STEM, I got to experience firsthand all the steps of publishing research. I learned how to use valuable resources dealing with remote sensing and land cover data.
Participating in NASA STEM really strengthened my understanding of data collection and analysis. It also exposed me to new concepts such as citizen science and AI.
Excellent. Our next Earth System Explorer project conducted research in area classification, iteration, and implementation of area classification AI for enhancing civil development.
This is a research on area classification, specifically on the iteration and implementation of area classification AI for enhancing civil development.
Hello, my name is David Ajao.
My name is Elle Bates.
I'm Nisha Bandari.
Hi, my name is Jackson Choi. I'm in grade 12 and I'm from Greenwich, Connecticut. We'd like to start off our presentation by giving some background information on our project. The textbook definition of urban development is the planning and executing of a city that will increase social and economic growth. Area classification is looking at an area and giving it descriptors. This can include how much water is in the area, how many trees, or in our case, whether the photo is of an urban, suburban, or rural area. This can be done on the Globe Observer app or website, or an individual can do it elsewhere. What is BRAILS? BRAILS stands for Building and Infrastructure Recognition using AI at large scale. BRAILS takes images and satellite data and outputs building features. This is especially useful for our project because we're determining urban sprawl based on images.
In the past few years, urbanization has increased at different rates throughout the U.S. due to stark differences in socioeconomic levels in different areas. In order to maximize the quality of life, predicting developmental and civil data is really important for urban planners.
Our goal was to train an AI model that would be able to predict urbanization trends based on photos taken by citizen scientists and satellites, as well as census data.
Our objectives can be split up into 3 parts. The first was collecting training data from our cohort's globe observer photos so that we could manually label them as rural, urban, and suburban. And the next part was actually training a model based on our data so it could classify an inputted photo as one of those 3 categories. And then currently we're working on applying certain Braille's functions combined with corresponding census data to generate more information. Now for our methodology, the first thing that we did was find and label 50 photos in each of our categories. Then we trained our model with the TensorFlow library. And then after this, we manually labeled which photos would be fit for Braille's and which weren't based on which ones had a clear building in them. And now we're working on supplementing our current model with the fine-tuned Braille's occupancy classifier and year-built classification. And we're making a function that outputs a score from 1 to 100 representing the urbanization level. And based on this, we'll also supplement some time series images from Landsat and socioeconomic data in order to plot current trends and predict future numbers, specifically looking at median income level and population.
Utilizing TensorFlow, our convolutional neural network intakes sample images and cross-references the images with our datasets of categorized images. It then produces a confidence level associated with each group's comparison and returns the classification with the highest accuracy, as well as the confidence score associated with it. On the left, we have our model's confusion matrix, which determines the accuracy of our trained model. For model validation, we tested 36 images for each category sourced from publicly available datasets to avoid any bias. The highest accuracy of 97% was found under the urban classification, likely due to the distinct nature of the architecture and development found in urban areas, while our weakest classification was found in suburban data and it was found to be 81%. On the right, we have another dataset, but our final general result was that our model is 90% accurate. Closely associated with the model accuracy, our model's confidence saw urban and rural areas be easier classified while suburban areas lagged behind. Given our small sample size due to the time limitations and planning caused by the unfortunate weather, we predict our model's accuracy could rise quickly given more sample data. Suburban data likely was harder for our model to distinguish as many of the features of suburbs such as greenery and architecture are often found both in urban and rural areas. Finally, when selecting photos, we try to use a wide variety of examples from each category, such as suburban roads and rural parks, as opposed to a specific house and other architecture for better model practicality.
Overall, the AI model we created using TensorFlow and Braille's was very accurate for classifying the photos into the categories urban, suburban, and rural. We can see that it was more accurate for urban and rural, but less accurate for suburban. And as David mentioned, the reason for this is that suburban is literally suburban, meaning it is in between rural and urban, and so the line differentiating the 3 starts to blur. The next step for us would be to add in the satellite data and photos as well as the census data to further train the AI. We would also set stricter parameters for suburban images to increase the accuracy. The product we have created, it can be utilized by urban planners and designers to create short and long-term projects based on the needs of the city and the AI and the data this AI model provides. The photos utilized in this project came from the Globe Observer app, and we'd also like to give a huge thank you to all of our amazing mentors. Thank you to Andrew Clark, Dr. Rusty Lowe, Peter Nelson, Cassie Stoffing, Roiba Adhi, and Osemarat Ojafa. And these are the many sources that we used. Thank you so much for listening to our presentation, and we hope you have a great rest of your day.
So please welcome the Earth System Explorer team with their research on harnessing citizen science to enhance land surface temperature prediction.
Good morning, everyone. Our team consists of Kevin, Candice, Suhani, Mako, Anna, Kay, Connor, and Aaron. Our project focus was on harnessing citizen science around the world to enhance land surface temperature prediction using machine learning models. To begin with context, the prevalence of urban heat islands have been drastically increasing over the last several decades. These areas are classified as having higher land surface temperatures compared to areas that experience less urbanization. While some people enjoy the higher temperatures, animals and our planet don't. This phenomenon can be attributed to the abundance of heat-absorbing impervious surfaces.
Rising heat could lead to a multitude of health issues. Heat illnesses, which are the health issues, can range from mild to deadly, and it is imperative to understand the severity of increasing LSDs and the effect that UHAs have on them. Our research question is how can we utilize machine learning model techniques such as the random forest and XGBoost models with citizen science data in order to enhance predictions of land surface temperatures. Our null hypothesis is that incorporating vegetation data from Globe Observer and Collect Earth Online data into the machine learning models will garner no significant changes to the accuracy of the model to predict land surface temperatures. The alternate hypothesis is that adding this data would create greater accuracy of the models.
46 interns in the Earth System Explorers team with 37 locations to use the Globe Observer app. Our group analyzed 958 sites and we uploaded them to an application called Zooniverse for citizen labeling. We sourced our temperature data for each site from the Landsat 8 satellite. The data was accessed with an open source code to extract LST for June 2024 as a daily mean. Then we used the Collect Earth Online platform to gain additional citizen source data for land cover. Collect Earth Online uses Sentinel to satellite imagery for each site an image was captured.
The graphic on the right provides a summary of our stages of data preparation. Throughout the process, we had to filter out a lot of inaccessible data. For example, many of the photos uploaded to Globe had not yet been processed or were not actually up photos. We were then able to feed this data to two machine learning models, Random Forest and XGBoost. These are the results for our Random Forest model. So we trained three models, one with coordinate data, one with coordinate and globe data, and one comprehensive model with coordinate, globe, and Collect Earth Online data. We then evaluated them with three statistical metrics, R-squared, root mean squared error, and mean absolute error. In summary, we found that Model 2 performs worse than Models 1 and 3, but adding in Collect Earth Online data to Model 2 to create Model 3 enhances the accuracy.
The three XGBoost models saw a similar trend to the Random Forest models. Model 1 was the most accurate model by a slight margin, followed by Model 3 and then Model 2. The addition of Collect Earth Online data greatly reduced prediction error. Interestingly, Globe Observer data actually served as a bottleneck for Model 2's performance. This bar graph shows the features our models use to predict land surface temperature measured using their F-score. F-score is a measure of the amount of times the features used to split data in any tree across the model. Longitude and latitude are by far the most used features, followed by 2 Globe Observer labels and then 3 CAO labels. We can consider the features with the highest F-scores to be the most important in predicting LST.
We were surprised to find that both of the models that used Globe Observer or Collect Earth Online data were slightly less accurate than our baseline models using coordinates. We also found that Random Forest models performed better than XGBoost models. There are a few sources of error that limited the predictive power of our models. Some images were poorly taken and had lower quality compared to the rest, resulting in less accurate labels. Second, our sample size was relatively small, containing less than a third of the possible photos. However, the addition of CEO data improved the accuracy between models 2 and 3.
In summary, we found that there is potentially a strong relationship between land cover and land surface temperature that would become more apparent if we address the sources of error in our study. We know from past studies that vegetation and other data correlate to land surface temperature, as is shown in the bottom right graph. Citizen science may play an important role in capturing this land cover data. Moreover, citizen science is particularly relevant because it encourages open science that could power global change. Further research on this topic is imperative to better understand the complex relationships between citizen-sourced land cover data, land surface temperatures, and urban heat islands.
Our research project was heavily influenced by the guidance of our mentors. We extend our thanks to each of them for their contributions. Additionally, we are grateful to the SEAS team and UT Austin's Center for Space Research for providing the resources necessary to make this project a reality.
These are our student and program reflections.
Excellent. So we want to invite all three Earth System Explorer teams to unmute their mics and turn on their cameras. Our first question is for Team 1. You had several programming aspects as part of your project. Did you come in with programming experience already, or was this something you learned while doing your project?
I can talk about this. I was the one who did basically all of the programming, and I had knowledge of R Studios, but I did not know any Python prior to SEAS. I learned all of it during the internship.
It seems like a great usage of land cover data. How else would we be able to use this data in other applications?
Well, expanding on our project, we can use the metadata that we gathered about elevation and longitude and latitude to create a map of like where trees impact power lines, so we can better predict where there's higher risk if there's a storm.
Excellent. Team number 2. What public data set did you find the most useful?
I can speak on this. So we definitely found that the Globe Observer data was the most useful. We took a bunch of photos and any data that we could gather, whether that was already pre-classified, and then we took it a step further to classify it ourselves. And so we definitely found Globe to be the most helpful for us.
Citizen science has become very important as evidenced by research presented. How can we engage more non-professional individuals in citizen science?
I guess I can talk about this also. We can definitely just encouraging people to go out and take these photos and go on and classify them as accurately as possible. That'll be super helpful to us. But then also just getting people excited to do science, and just when they notice something to seem a little bit different, to go on and report that, whether that be in the Globe Observer app or somewhere else. So I think it'd be super important for them.
Great. Team number 3. How has this process changed the way you view the use of AI in science?
I can speak on this. So, I didn't really know how AI could be used in science. I thought it would be more for software use and stuff, but being able to use data that comes from the public through AI to produce real results is definitely something new that I didn't realize.
And also for team number 3, what was the most difficult aspect of your project?
I can speak on this again. So another difficult part of our project was actually seeing what Globe Observer pictures were accessible for us. A lot of there were so many pictures that we could use, but only half of them could be utilized to put through the machine learning models because they were either obstructions, or they weren't actually down photos, or they just weren't loading through the program. So that was one of the hardest parts of our project.
Great. Well, you all did an excellent job. So we will continue with the Earth System Explorer teams. Our next team researched creating a model to predict high-risk areas for flash flooding in our urban areas of Houston, Texas.
Floods are quite unpredictable, and current flood maps have some flaws. One of their biggest flaws is the lack of consideration towards pluvial flooding, precipitation flooding that can turn into a flash flood. Urban areas are the most affected because the precipitation cannot absorb into impervious surfaces. There's limited research on pluvial flooding, since urban infrastructure varies from city to city. So when the flooding happens, the residents are ill-informed. Using the Globe Observer database and QGIS analysis tools, we developed a model that will help predict areas in Houston, Texas, that are at high risk for pluvial flooding to better inform the residents in the area.
To generate accurate and clean data that can be fed into the 3D model simulator, we used the AOI points that contain images of the north, west, east, and south of various points in the area. In order to extract the important slope data that we wanted to get, we ran a series of steps. First, we performed semantic segmentation using the UNet architecture. This segmentation algorithm separates the ground from all other objects. Once we've identified the ground, we run a SIFT detection algorithm that gives us a series of points in the image. In order to get the 3D information of these points, we run a monocular depth estimation algorithm, Zoe depth, which also gives us a 3D mesh reconstruction. Finally, we interpolate the points around the features, ultimately building a dataset of elevation nuances on the ground.
Using QGIS, we can create a DEM, or a digital elevation model, with the data taken from the AOIs to simulate the flash floods on. The AOI data points, however, only cover a small percent of the area needed to make an accurate simulation. As such, we can use the Open Topography plugin on QGIS, and from a DEM of the Houston area, we can take around 10,000 elevation points, as you can see in the top left picture. X is longitude, Y is latitude, and Z is elevation. We can use this to interpolate it with the AOI data. Afterwards, we can use TIN interpolation to create a DEM using the satellite points and AOI points, as you can see in the bottom right.
To analyze the DEMs, we applied a Python D8 flow algorithm. The D8 flow algorithm determines the flow direction based on the direction of steepest descent at each elevation cell, and assigns an 8-bit integer based on the shown grid. East is 1, southeast is 2, and going counterclockwise around, we multiply by 2 each time until we arrive at 128 for northeast. For instance, if the steepest descent from a cell is northwest, shown in the green, it gets direction code 32. A benefit of this labeling system is also that it allows for combining multiple directions of equal descent. A cell flowing equally northeast and southeast, shown in blue, will get the value 130 because of 128 for northeast is added to 2 for southeast. This way we can represent flow out of a cell using a single 8-bit integer for each cell. To illustrate, consider a 5x5 elevation data table on the left. Arrows in each cell indicate the steepest descent direction, indicating water flow. On a corresponding table on the right, cells are relabeled based on their flow direction codes. The main goal of this is to measure flow accumulation, which indicates how many cells contribute flow to a specific cell. For example, this cell's value of 17 on the accumulation plot indicates that 17 cells worth of water are flowing into this one cell, showing where water will pool in case of a flash flood. Using Google Colab, we applied this D8 flow in the Houston AOIs, then plotted it using Python's matplotlib. In this example, AOI 3 in Houston, the left graph shows a standard elevation graph using the raw elevation data from the DEM. On the right, the graph shows a color-coded direction map, where each color represents a different direction code from 1 to 255. Finally, these two graphs depict the flow accumulation in both linear and logarithmic color bars. Here, for this specific AOI, we can observe that the water seems to pool in the roads.
In order to make this tool accessible, we made a website that allows users to select areas in Houston to simulate the flash flooding on. We used Flask for backend development in Python. The AOI points for Houston were imported via a CSV file into a SQLite database. The Flask application used SQL queries to retrieve the points from the database. Users could select and deselect points on the map. This feature was added in the front end with leaflet.js. After confirming the points, a DM of the selected points would appear on the website and users could simulate flash floods on the model, which would reflect how flash floods would occur at that AOI location. The website is a very useful tool to publicly implement the resource we created and aid with flash flood preparation for those living in that AOI area.
With this tool, users can see which areas have high risk of flooding in Houston, Texas. Since we can also simulate the flowing of the water as well as where it will end up, this tool will allow developers and homeowners to keep themselves safe. In the future, this research can be expanded on to make this more general, so every developed area in the country can go through flooding simulations. The limitations of this project can also be improved on, as the accuracy of the civilian-taken data in the form of AOIs and QGIS's plugins lends the project a degree of inaccuracy. As such, in the future, more reliable tools and data can be used in order to make more accurate DEMs to run simulations on. We would like to thank our peer mentors and teachers for guiding us throughout our research and our internship. Thank you for all your support.
Great job. Please welcome the Earth System Explorer team predicting wildfire risk based on land cover classification and past wildfire data in California.
Hello, everyone. Our project is predicting wildfire risk based on land cover classification and past wildfire data in California. Our team members are Atharva, Akshita, Ananya, and Christina. Wildfires are becoming more frequent and severe due to climate change and human activities. These fires cause significant loss of life, property, and biodiversity, while also having long-term effects on ecosystems and air quality. The financial burden of wildfires includes not only the immediate costs of firefighting and damage repair, but also the economic losses from disrupted communities and businesses. Our research question is, what are the key structural components of land cover that most significantly influence fire danger, and how can they be effectively identified using the Globe Observer app and historical fires? Our main objective is to find correlations between land cover types and wildfire risk.
Now on to methodology. Our project uses data from past California wildfires to predict fire risk. We used historical and land cover types such as forests, grasslands, shrublands, urban, and bodies of water. Our algorithm analyzes if there's correlation between certain land cover types and the risk of fire. Our dataset, which was taken from ArcGIS, was split into 3 categories or strata of very high risk of wildfire, relatively moderate risk of wildfire, and very low risk of wildfire. A sample of 33 randomly selected points was taken from each strata as well. These values were then fed into the FEMA wildfire risk map, which gave us information on the wildfire risk at that exact location. After identifying our main points, we utilized the location photos, north, south, east, and west, and labeled the type of land cover found at that location.
Now looking at the data and model, as Akshata mentioned before, so we have the FEMA risk map, which we use to identify the risk, the wildfire risk in every coordinate, and then we have the machine learning model, which we use for predictive analysis. So here are our results. So on the left side, you can see the chart, which shows that wildfires actually had a low to moderate risk in forest areas and a high risk rate in urban areas, which was really interesting to us because we expected forests to have a high risk rate because due to its easy spread. But upon further research, we realized that in forests there's a lot of humidity, which prevents wildfires from going on. And in urban areas, there's a lot of tools and gas pipes, etc., which can lead to combustion and quick spontaneous fires. The graph on the right kind of highlights the significance of the land cover classification versus the significance of the historical fires. And you can clearly see that land cover classification plays a much bigger role in predicting wildfire risk. So for our classification technique, we used random forest to help with the classification model. And basically, our classification task, the result is the wildfire risk category, which is chosen by most trees. And the random forests actually help prevent overfitting, which can be a common issue with individual decision trees. And it kind of ensures that our model can be used anywhere else, not just in California. And our model had a 75% accuracy. So it was able to kind of predict things and really find a pattern between our data.
So through our work, we discovered that there is a direct relation between the type of land cover and the associated fire risk. For example, forests generally exhibit low to relatively low risk, whereas shrublands and grasslands demonstrate a relatively high to a very high risk. Urban areas actually have a varying level of risk from moderately high to very high, mostly depending on their location and population density. Finally, wetlands and bodies of waters present moderately high to relatively high wildfire risk. And on behalf of my team, I would like to thank Margaret Baggio and Selena Miller from the Center for Space Research, as well as the 2024 Earth Science Explorers Advisors, Dr. Peter Nelson, Dr. Russan Lowe, Dr. Cassie Sofing, and Andrew Clark, as well as our working team mentors, Andrew and Benjamin, for helping us with this project. And some highlights from this experience. Obviously, we got a lot of support from our mentors, and there are plenty of resources for our project. One challenge was definitely coordinating meetings across different time zones and schedules.
We would like to thank NASA SEAS and express our gratitude for this wonderful opportunity. Thank you very much.
Hi everyone, we're working group 4 and I'm Abhiram Raju.
I'm Sophia Myers.
I'm Hubert Pye. I'm Noah Perez.
And I'm Anna Schiffman.
Over the past few weeks, we have worked on a research project, remote sensing correlations between income and land cover to analyze urban heat islands in Austin, Texas. Our goal with this research was to investigate what factors affect the formation of urban heat islands and how they correlate with each other. Through this, we hope to shed light on income land cover patterns to potentially assist future urban planning.
Every year, NASA sees interns choose an area of interest, AOI, of 37 points to classify based on land cover. We utilize the 14 AOIs in Austin, Texas from 2022 to 2024 and use the land cover data to investigate how factors such as impervious surfaces, which is concrete and asphalt, greenness, and median household income affect the formation of urban heat islands, UHIs, the phenomenon in which certain areas of a city experience extreme heat at a higher rate than others. We expected to find that as land surface temperature and percentage of impervious surfaces increase, greenness and median household income would decrease.
We derived our datasets from 3 different sources for this project. We obtained our percentages of greenness and impervious surfaces for each AOI from the Globe Observer database via Collect Earth Online, and we used the same to collect on-the-ground photos from each AOI to validate our land cover data. We use NASA Appears to request land surface temperature data, or LST data, for our AOIs from the EcoStress instrument on the International Space Station. Finally, we use the United States Census Bureau to find datasets showing the mean and median household incomes for the city of Austin.
Cross-checking land data with global observers help create variations in remote sensing data. This identification allows for local variations and for researchers to cover large areas and obtain more frequent updates.
We used k-means clustering, an unsupervised machine learning model, to classify UHIs in our study. To find the optimal number of clusters, we evaluated the silhouette score, Davis-Bouldin index, and Kalinske-Haribas index, which indicated that 2 clusters were the best fit. On the right, you can see the clustering result where each coordinate is grouped into high or low UHI risk. Our analysis showed that socioeconomically disadvantaged areas have higher risk of being UHIs. This is evident in the left graph, which compares the mean income values by risk level, showing that high-risk areas have lower median and average incomes. The right graph highlights the environmental factors, demonstrating that high-risk areas have less vegetation and more impervious surfaces, contributing to higher UHI risk.
We also carried out hierarchical clustering. The left plot here displays the results of the clustering analysis on our AOIs. Here, after calculating the same indexes for hierarchical clusters, the optimal number was 3 clusters. So 0, 1, and 2 represent high, low, and medium risk respectively. On the right, we've also generated pie plots for every variable to show the distributions and interactions between them. And over here, the top 2 graphs depict the continuous distribution for the entire data set, while the bottom 2 graphs display the bar charts for income and land cover cluster-wise. The high-risk cluster has low incomes and vegetation, but high impervious surface percentages. But the low-risk cluster, on the other hand, has high incomes and vegetation, but low impervious surface percentages. This shows how our clustering helped unravel trends in the data to identify areas at risk of becoming UHIs.
We also use dbScan because it handles noise and outliers well, which is especially useful when working with real-world data. As displayed, the clusters formed or differentiated within specific AOI points, unlike what we saw in k-means. In these clusters, we found that as income increased, so did vegetation, and in areas with lower income, there were, on average, more impervious surfaces. This is especially apparent in clusters 0 and 1, which follow the trend described previously. We hypothesized that UHI risk would increase with a higher percentage of impervious surfaces and decrease with increased greenness and median income. Regression analysis confirmed our hypothesis about the relationships. We found that there was a weak negative correlation with a p-value of 0.002 between impervious surfaces and income, and weak positive correlation with a p-value of 6 times 10 to the power of negative 18 between greenness and income. However, we want to note that once land surface temperatures were included, the data set was very incomplete. The clustering algorithms were not as effective in describing trends, and LST actually had very minimal correlations with the other variables, as it was relatively consistent throughout Austin. And thus, we want to strengthen our research in the future by expanding to California for a more diverse data set.
There are several potential sources of error in our project that may have affected our final correlations. The eco-stress instrument takes LST measurements at different times of day, so the timing for each data point was not consistent. 2 AOIs lacked impervious and greenness data, and some AOI points did not have corresponding ground photos on Globe Observer, preventing us from cross-checking them. Overall, our team members said that the NASA STEM internship allowed us to enhance our skills, learn what a STEM career might look like in practice, and make meaningful connections with like-minded individuals. The unique challenges presented helps us grow as people and scientists, too.
We'd like to thank everyone who helped for the contributions. Please scan the QR codes to explore all the data sets and to view our detailed poster.
Excellent. So we invite all 3 teams to please turn on your cameras and unmute your mics. We have several questions. The first is for team number 1. How did you decide on using the UNet algorithm for semantic segmentation?
So there are a few algorithms that have been, so UNet isn't an algorithm, it's a neural network. And there are a few that have been trained for semantic segmentation. How I picked the best one was based on how much computational power was needed, and then also how accurate it was.
What is the difference between linear and logarithmic data?
So I assume you mean like for the graphs at the end, those aren't different types of data. They're the same data set, but they're just shown in color bars, where one is a linear color bar, meaning that equal data differences have the equal color differences, and then a linear color bar is where differences in elevation towards the lower end are more pronounced than those on the higher end.
And for team number 2, was there a reason that you chose the years 2000 to 2018 data set range?
I can answer that. So basically, we had to go through like the California wildfire kind of like website where we got the official data for that. And through that, we searched through like multiple like wildfire timeframes, and we found that from 2000 to 2018, we got like the most detailed maps rather than later or earlier like wildfires.
Also, for team number 2, what would you suggest to urban areas to mitigate the risk of fires?
I can take this. So on one hand, a lot of the reason wildfires start is because people leave debris in their yards, like leaves and firewood, or even just like twigs can get a spark and then start a fire. So on one hand, people should make sure to clear these out, and also spacing trees, because sometimes when they're very close together, they can make it easier for fire to spread. And then one more suggestion is to make sure that there's a lot of advisory for people so they are careful, especially when using grills, sometimes bonfires. I think a large portion of fires are actually started by humans. So
Great. Team number 3, this was excellent data. Earthquakes and fires are number 1 and number 2 natural disasters. Based on your data, how can California reduce the risk of wildfires?
Yeah, I can try taking this question. So, based on the data we found about urban heat islands, we're actually planning on expanding our project to California in the next week before July 31st. So, we might be able to provide a more concrete answer then. But based on the correlations we found, it looks like increasing the amount of vegetation leads to just overall cooler land surface temperatures. And I would imagine in urban areas specifically, that would decrease the risk of extreme heat events for a lot of the people living there. So increased vegetation, but then of course, like the other, like working group 3, team 2 mentioned, having dry vegetation and dry brush and twigs is also a big risk. So there's definitely a balance to mitigate there.
And also for team number 3, what were some of the major challenges you faced gathering data and how did you overcome them?
I can answer this one. So we tried a bunch of different data sets to get the best data that we could, especially with their time constraint. And we had a lot of difficulties getting LST data, and there were also many holes in the MODIS satellite data. So we definitely had a little bit of trouble loading it to make sure we would get the most accurate results possible.
Great. Well, thank you all. Congratulations. Excellent job on your research. Our next Earth System Explorer team is analyzing the impact of solar arrays on surrounding vegetation in agrivoltaic farming for optimization of performance.
Hello, our names are Yuki Chen, Ethan Poon, Eric Middleman, Michael Manders, Enyan Perales, Arjun Nair, and Joanne Miranda, and we are the Agro-Vol team as a part of the Earth Systems Explorers. Our project is analyzing the impact of solar arrays on surrounding vegetation in agrivoltaic farming for optimization of performance. Agrivoltaics, also known as low-impact solar, is the practice of using the same land for both agriculture and solar energy production. It offers an alternative to the complete conversion of agricultural land to solar locations. This co-location practice has the potential to both address energy inequity by supplying solar energy in locations less centered on the electricity grid, while also helping farmers diversify income through land lease payments and other business models. Agrivoltaics can sustain rural farmland economies, which have an especially growing need for support. Further, only 2% of the large solar arrays in the U.S. are agrivoltaic, highlighting the potential for growth of this practice.
The success of agrivoltaics relies on optimizing the balance between energy production and agricultural output. Solar panels can create microclimates, which can significantly affect plant growth. Our research question is, by using remote sensing tools and satellite data, is it possible to analyze the impact of solar arrays on surrounding vegetation health in order to inform and facilitate the future and success of agrivoltaic projects?
We approached this question by outlining the data of interest. Our first step was identifying agrivoltaic solar projects in the U.S. We first sorted through the Globe Observer AOI points to identify areas with solar panels and overlaid them with the U.S. Solar Photovoltaic Database and filtered to find agrivoltaic projects. After identifying these specific locations on the USPVDB, we matched them up with data on the Landsat database. By inputting the location into the Landsat Time Observer, we were able to identify our locations of interest and extract the data.
We then decided to use the NDVI spectral wavelengths and TCG data from the Landsat satellite to identify any trends occurring after the installation of the solar array. The NDVI estimates the amount and health of vegetation on the land. Band 4 shows the red wavelengths. Less reflected red light means more photosynthesis is taking place. The TCG shows photosynthetically active vegetation. We use the Landsat time series to allow us to access and download data from specific agricultural solar farms. After downloading the CSV files from multiple sites, it is then separated by measurement type. Then a Python program is run on the collection of CSV files to combine their data. The program starts by parsing the raw data from the CSV file. Using the construction year from the metadata, it takes a snapshot from 15 years prior to the construction to up to 10 years after the construction. This effectively centers the data around the construction year. It then averages the data from all the measurements and outputs that to be graphed in Excel.
The NDVI data showed a decrease of 18.5% after the installation of solar panels, indicating that vegetation health decreases with the implementation of agro-voltaics. Data showed that band 4 decreases by 40.6% after installation of solar panels, indicating that photosynthesis increased after implementation of agro-voltaics. This can likely be attributed to increase in red light absorption from the solar panels.
Data showed that TCG decreased by 54.2% after the installation of solar panels, indicating that photosynthesis decreased after implementation of agrivoltaics, signaling possible vegetation health decrease.
The decrease in NDVI and TCG suggests a decline in overall vegetation health and photosynthetic activity following the installation of the solar panels. However, decrease in band 4 suggests increased energy use under the conditions created by the agrivoltaic arrays. This research shows that the complex interactions between solar arrays and surrounding vegetation and will aid farmers and energy producers by contributing to the sustainable growth of agrivoltaics. In terms of future research, we expect to create an application interface to predict solar power potential or solar exposure in our area. Our tool will further optimize best land usage for efficiency in energy and vegetation growth. We also want to explore variation in agrivoltaic farms and attribute changes to conditions, such as sun angle, panel area, location, along with its relevance to weather. Determining what factors can influence values like B4 and NDVI can be essential for future research.
The best features of this year's internship was that we were able to pursue our own projects based on our interests, which allowed us to work with what we were passionate about. The main challenge that we experienced was trying to fit our research goals into the short time frame that we had.
Overall, we all reflect that the SEAS program both gave us insight into different fields of earth science and provided us with mentors that allowed us to explore our passions deeper.
We would like to thank our SEAS ESE mentors Rusty Lowe, Cassie Sofing, Peter Nelson, and Andrew Clark, and the NASA SEAS program for providing us this opportunity to conduct research in this program. Thank you.
Thank you.
Thank you.
So our next Earth System Explorer project is on drought monitoring and prediction using the Globe Observer app in Los Angeles, California.
Hi, my name is Benjamin Lee, and my project is Drought Monitoring and Prediction in Los Angeles, California. Droughts are something that impact people all across the world, and especially in California and in Southern California, where I live in Los Angeles. Millions of residents suffer in their daily life due to drought from water shortages affecting their daily life. And my goal in this project was to monitor and predict drought patterns in Los Angeles using satellite and local data. So the research question that spurred my project forward was, how can we monitor and correlate drought patterns and the cause of drought in Los Angeles, California through data resources? The background info going into this project is my use of how California classifies their drought conditions, which is managed by agencies such as the Department of Water Resources. The levels are categorized through normal, alert, emergency, and severe. And I look towards times in Los Angeles when drought levels were at emergency or severe. What's being studied are factors that can influence drought, and this is from local and satellite data. The area of study is the greater Los Angeles area, with coordinates being around 34.09342 north, 118.25187 west, 34.052235 north, and 118.24368 west. My methodology going towards this project was using data collection tools such as vital signs from NASA's Earth Now, NASA's Landsat data, California's Water Watch, and NASA's Worldview Earth data. And for my usage of these tools, I track signs of anything that may impact drought levels in Los Angeles area, such as reduced soil moisture and low precipitation rates. And I track these signs and match them to times when drought levels were at emergency or severe. So in terms of time schedules, I tracked 3 times when drought levels were extremely high in Los Angeles, which were July 2015, June 2016, and August 2021, and compared them to a non-drought season time in September 2023. Now, if we look at the times of drought that I proposed in the 3, the soil moisture content is extremely low, with July 2015, June 2016, and August 2021 all being around 0.05 centimeters cubed per centimeter cubed in terms of moisture saturation in Los Angeles. Compare that to September 2023, where the moisture saturation was actually 0.37 centimeters cubed. And also, if we compare precipitation rates, July 2015 and June 2016 served only 10%, while August 2021 was even lower with only 5%, while September 2023 shot past the average precipitation rate with over 40%. So my findings going into this project were that drought seasons and periods of droughts are followed by factors such as low soil moisture and low precipitation rate. This also goes for the opposite with high soil moisture content and high precipitation rates following non-drought seasons. I also found that satellite data and local data can be used together to forecast periods of drought and help people prepare for the future. Some challenges I had going forward in this project were the geographic limitations only staying in the Los Angeles area. I think that if I spread towards California, it might give more accurate results. Data availability and completeness and technical challenges just with not having data for a specific time periods, as well as analytical limitations. But the conclusion at the end of the day is that drought is a serious problem affecting the Los Angeles area, but certain factors that correlate to it can be tracked with data and help towards the future. For what's next, I want to try seeing if this can work in real time by regularly checking satellite and local data sources for patterns, and see if this can also translate for after effects of drought, such as wildfires. I also want to consider factors such as El Nino and past drought seasons. So thank you for everyone who made SEAS 2024 possible, to all sponsors, and I would like to thank Ms. Kai Silfing, Mr. Peter Nelson, Dr. Rusty Lowe, Mr. Orst Nojifa, and my parents for helping me along the way. Thank you.
Please welcome the next Earth System Explorer team with their research on CS flare, citizen science, fire likelihood, and risk evaluation.
Hey everyone, we're the Earth Systems Explorers CS Flare team, also known as Citizen Science, Fire Likelihood, and Risk Evaluation.
So let's start by talking a little bit about why wildfires are such an important issue. While many of us often associate wildfires with rural and uninhabited areas, they actually cause high levels of damage to both urban and suburban areas as well. In fact, in 2023, over 3,000 homes were destroyed by wildfires and over 2 million acres of land were burned in the United States. We wanted to pursue a project that would allow the general public to be more involved in the wildfire risk management of their own homes and suburbs.
Applying the knowledge we learned throughout the course of the SEAS program, we asked ourselves, how can we utilize the Globe Observer database and satellite imagery to create a tool that provides users a greater understanding of wildfire risk on a community level? Our answer to that question is CS Flare.
Our goals for CS Flare are to inform citizens of fire likelihood and tips for wildfire prevention in their area, and to effectively use existing satellite data and machine learning models.
We wanted to enable citizens to take the initiative in protecting themselves and their communities. Through citizen science, we wanted to make satellite data available to everyone via a personalized fire risk evaluation. On top of that, users will be able to get advice from reputed resources on lowering that score. So, we decided to make an app.
CS Flare begins when a user takes 5 pictures, 4 in the cardinal directions and 1 downwards. Once the pictures are taken, they're then identified using a machine learning model to identify potential fire hazards, like dried brush or grass dryness levels. Before calculating the final fire score, environmental indicators from satellite data are also considered. These factors are then combined to determine the final fire risk score. Finally, the app displays the score along with recommendations to improve it.
To plan out the creation of our app, we created a wireframe using Figma. After the user uploads their images, they will be able to explore the exact risk found in their pictures and be recommended advice to lower those risks. The development of the app has progressed in the Flutter framework, programmed in the Dart language, and we plan to use TensorFlow Lite to integrate the AI models.
We trained the Google Teachable Machine on downward images on the Globe Observer land cover dataset to classify vegetation dryness. As it's seen on the left, we were able to create a model that analyzes grass moisture on a high accuracy. We also created the fire risk factor assessment by fine-tuning the YOLO V8 image segmentation model on the north, east, south, and west images from the Globe Observer database. The output of the model, shown on the right, precisely segments vegetation in a variety of environments, proving effective in identifying high-risk wildfire threats.
CS Flare is able to accurately recognize significant fire risks surrounding the user's location, as well as a fire risk rating determined by satellite data regarding the user's area of interest. Using machine learning models trained by Globe Observer data, users can detect environmental factors at high accuracy and provide them with relevant information about how they could reduce fire risk around them.
CS Flare's strengths include its ability to leverage reliable data from the Globe Observer database and provide a comprehensive risk assessment by analyzing multiple environmental factors using advanced image segmentation models. Some weaknesses include its focus on a limited set of environmental factors and dependency on the quality and availability of citizen science data. In the future, we hope to collaborate with local government agencies to expand the app's capabilities.
Amongst our reflections, getting the opportunity to work with equally passionate students allowed us to develop our collaboration skills while also learning about different approaches to scientific research. Furthermore, lectures from reputed scientists such as Dr. Burdest, Dr. Yang, and Dr. Lind helped us gain essential insights. As a whole, the opportunity to create our own science identities and projects definitely made this experience unique and memorable.
And finally, a very big thank you to everyone who helped us with this project, our ESC mentors, peer mentors, the CSRC staff, and the partners of the NASA SEAS program. Thank you.
So we invite all 3 teams to please turn on your cameras and unmute your microphones. We have a question for team number 1. This is such an innovative idea. How did you decide to come up with this research topic?
I can answer that question. So us as a team, we were very interested in renewable energies and how we can improve the performance of them. So we wanted to look into what truly affects renewable energies and what communities could benefit from the improvement of them. And that's how we decided on rural areas and their agrivoltaics, because vegetation around agrivoltaics highly impacts the performance. And of course, the success of agrivoltaics can truly improve quality of life and the success of these rural communities. So I think the main reason that we chose this was driven by kind of wanting to do good and being able to do research that can impact the communities that we care for through a scientific topic that we care for. So through brainstorming, we decided that this was the best way to do that.
Great. When studying solar arrays and vegetative growth, what is the average size of the area that your team studied? Team number 1.
The average size of the area that we studied is about 1 kilometer squared.
Perfect. Team number 2, there's a lot going on in California. What would you prioritize as a specific future area of study?
As a future area, I would say for my current project, I focused a lot on the Los Angeles area, but maybe going more north towards San Diego would be another area of interest for my research.
And team number 3, what are some major challenges you faced gathering data and how did you overcome them?
I can answer that question. So a lot of the databases that we went through were the Globe Observer, a lot of the NASA data sets, and we really had a little bit of a struggle being able to process that data to make it into a form that we can actually use. So a large part of our research process was actually getting the data from the Globe Observer app, labeling it, and finding the right tools that we can use to make sure that data goes into the right place. But with a lot of research and guidance from our mentors, we were able to do just that.
So for any of the teams that want to respond, a lot of these projects do focus on California. How and to what extent could they be applied to other areas of the United States and even the world?
So drought is a problem that affects many areas of the world, and this project can be utilized wherever satellites such as SMAP do focus on factors such as soil moisture and wherever there's local data to use to track factors on drought. So it's a project that can be spread worldwide wherever is needed.
Great. Well, you all did an excellent job. Congratulations on your research, and I learned a lot from you. We will take a 20-minute break. We invite you to watch highlights on student accomplishments during the Earth and Space Science course. Our thanks to Asha Carmichael for scoring and preparing these highlights. We will reconvene at 12:20 with session 2 of the SEAS Science Symposium. Welcome back for session 2 of the SEAS Science Symposium. Our next presentations are from the Galaxy Classification team, led by their mentor, Dr. Judith Reese. Dr. Reese has conducted research on near-Earth asteroids at the McDonnell Observatory and continues to be committed to the SEAS program. Our first presentation will be research conducted about mapping the Milky Way.
Hello, we are the Galaxy Classification team for the NASA STEM 2024 internship program, and our project is on Gaia-Vari mapping the Milky Way.
Hi, my name is David Yang, and I'm from Fairfax, Virginia.
My name is Rishi Tripathi, and I'm from Mansfield, Massachusetts.
Hi, my name is Natalie Bell, and I'm from Temple, Texas.
We had 3 goals for this project. Our team wanted to look at the frequency and distribution of the different variables in our Milky Way. We did this by using the data we acquired from Gaia. Next, we used the parallax measured for each of the subjects to calculate the distances to the variables. We did this to determine the absolute magnitudes of the variables. Lastly, we determined a period-luminosity relationship for a specific type of pulsating variable, which we then compared to the previously observed relationships found in previous studies done by researchers. Types of variables. Cepheids, aurora Lyrae, long period, and delta Scuti are all different types of pulsating stars. This means that they expand and contract periodically. So the picture on the right is an example of a pulsating star. The eclipsing and ellipsoidal binary systems are not just one star, but a system of stars. The picture on the bottom right is a binary system. So this will also be expanded upon later in our presentation. Physical properties. The way we classify all the data received by Gaia is by looking at the properties of the variables and comparing them to perfect examples. Apparent magnitude is how bright an object looks as viewed from the Gaia spacecraft. Absolute magnitude is how bright an object looks when viewed from 10 parsecs away. 10 parsecs is around 32.6 light years away, which is around 192 trillion miles away. So it's very far. And the period is the time it takes for the star to complete one full cycle of its brightness variation. So the contraction and expansion makes the star dimmer and brighter respectively. Parallax. Parallax is the observed displacement of an object caused by the change of the observer's point of view. This change in point of view is caused by the Earth's movement around the Sun. It's a great method of measuring distances to these variables, which greatly helps us map the Milky Way. This will also be expanded upon later in our presentation.
Okay, to begin, I will be describing the process that we used when classifying the different types of variables. First, we worked to classify Cepheid type pulsators, which are pulsating variable stars. On the slide is an image of one of the Cepheids that we classified. This image shows that this specific Cepheid has a period of 1 day and 20 hours, which aligns with the average of 1 to 200 days for Cepheids. This image also includes a diagram that helps us determine the color value of a specific subject, which is typically 0.2 to 2.3 for Cepheids. You also notice that there is a distance modulus on this image. This will be explained further by David later on in this presentation. On this slide, we also included an HR diagram, or Hertzsprung-Russell diagram, that we use to determine the absolute magnitude of Cepheids, which is usually -6 to 0. On the slide, Well, lastly, we included an image that shows multiple examples provided by Gaia that we utilized while classifying variables. Okay, next we work to classify our Lyrae type pulsators, which are also pulsating variable stars. Our Lyrae type pulsators typically have a variability period of 0.2 to 1 days, an absolute magnitude range of -1 to 1.5, and a color value of 0.3 to 1. Okay. We then work to classify delta Scuti type pulsators, which are pulsating variable stars with variability period of 0.02 to 0.3 days or 0.5 to 7 hours. We also classified long period variables, which are also pulsating variable stars, but with long variability periods of 10 to 1,000 days. Okay. Lastly, we classified eclipsing binary systems, which consist of two closely orbiting stars that have an absolute magnitude range of 2 to 7, and ellipsoidal binary systems, which consist of two close stars moving in an elliptical orbit with an absolute magnitude ranges that are typically -1 to 10. This next slide includes a pie chart that shows the distribution of the 374 different variables that we classified. Of these variables, Cepheids are the least common, but the most important. They're the best standard candles and are used for distance determination for very distant objects, for which the parallax is not measurable. They have a period luminosity relationship in which their variability period is closely related to their luminosity. And delta Scuti type pulsators are our Lyrae type pulsators, and long period variables can also be used for distance determination if Cepheids are not present.
So now that we've classified our Cephids, what we can do with them is we can calculate their absolute magnitudes. And why their absolute magnitudes are important is because, as Natalie mentioned earlier, Cephids tend to follow a period luminosity relationship, or there is a positive correlation between the length of their pulsation period and their absolute magnitude, which is just a measure of their intrinsic brightness. And so in order to find their absolute magnitude, first we need to find their distance. And this we do through the parallax method, as mentioned earlier. As you can recall, the distance in parsecs is equal to the reciprocal of the parallax angle in arcseconds. And after getting the distance, we can also find the apparent magnitude. And this is basically just the average brightness that the Gaia telescope records when viewing the star. And so once we have the distance and the apparent magnitude, we can plug this into the distance modulus equation from earlier and use this to solve for the absolute magnitude. And this is what we did for each of our Cephid variables that we classified. And so looking here, we were able to plot it on our own Cephid period luminosity relationship. You can see that there's a positive trend in terms of the log of the period and the absolute magnitude. Our graph is the one on the left. You can see it follows a similar upward trend as the graph on the right, which is a study taken by the Hubble Space Telescope, and it was observing several nearby Cephids. Also for our graph, you may notice that we have 20 Cephids plotted, which is more than the 7 we classified. And the reason for that is we added 13 previously classified Cephids to our data set in order to improve the accuracy. And as for the accuracy of our own Cephid period luminosity relationship, we looked at a different study by Lazovic et al., which also established a period luminosity relationship. And the slope of their trend line was negative 2.67 plus minus 0.17. And our own empirical slope for our trend line was negative 2.65 plus minus 0.477. So very close with a percent error of only 0.75%. However, where our trend lines deviated was in the y-intercept. The established one was negative 1.58, and our empirical y-intercept was negative 0.495. And so there are a couple different reasons for this error. One is that we used a smaller sample size. We only used 20. And so there's a chance that this sample wasn't a good representation of all the CFIDs out there. In addition, we didn't have any spectroscopy data from Gaia. And why this is important is there's actually two different types of CFID variables. There's type 1 and there's type 2. And they are made out of slightly different elements that would be able to be distinguished on if we had spectroscopy data. And these type 1 and type 2 type 1 and type 2 CFIDs display slightly different period luminosity relationships. And so there is a chance that our graph is slightly skewed, as edge cases from type 1 and type 2 could have served to slightly skew the data. Finally, another reason for the error is that studies have shown that there can be a slight inconsistency with the CFID period luminosity relationship depending on where they are in the galaxy. So the CFIDs in our galaxy may demonstrate a slightly different relationship from CFIDs in another galaxy. However, this discrepancy isn't big enough to discount their usage in calculating distances, so we still use CFIDs. Now moving on to our RR Lyrae variables. We also attempted to do the same thing at establishing a period luminosity relationship between the log of their period and their absolute magnitude. However, as you can see here, there really wasn't a great correlation between period and absolute magnitude like we had with the CFIDs, at least in the visible light wavelength, which is what we were observing. So rather than try and establish a positive correlation, what we did instead was calculate a range of distance errors given an apparent magnitude. And so as you can see here, given different apparent magnitudes or apparent brightnesses from Earth, we can calculate a range, a distance range in which this R Lyrae variable might be located. And as you can see here, as the apparent magnitude increases, which just means that the star gets dimmer as it appears to us, the range and distance increases. So this means that there is a greater error margin in which our distance calculation is in. And you can see this in the graph as well. The higher the apparent magnitude, the larger the distance between the possible minimum and maximum distance. And we calculated these errors using the standard deviations of the absolute magnitudes, and we used that to calculate our error for the distances. Moving on to applications of our research. So one of the main goals of Gaia is to understand our own galaxy better and ultimately create a three-dimensional model of our Milky Way that can be used for many different purposes. And so our research helps with that by being able to calculate accurate distances within our own galaxy so that we're able to map the location and distances of different stars or systems. In addition, our research helps to establish a cosmic scale and measure distances outside of our galaxy as well. So this is with the CFID period luminosity relationship. Even though there were some errors with our own findings, it was close enough that using such a relationship would be able to produce a reasonably accurate estimate for distances outside of our own galaxy. At the very least, a lot more accurate than parallax methods at that distance. And finally, it helps us understand the distribution of the different variable systems and stars in our Milky Way galaxy. So this is what we did earlier with the statistics. We're able to find the general trend of which stars and which systems are rarer than the others. And if you can see here on the right, the photo on the top was a CFID variable discovered by Edwin Hubble in 1923, and it was later revisited by the Hubble telescope in 2010. And you can see it's a CFID in how the brightness pulsates over time. You can see it starts off dimmer and it gets brighter over time. And this is actually a CFID found in the Andromeda galaxy, which is further away than our own galaxy. And so you can see that CFIDs are able to calculate, we are able to use CFIDs to calculate distances in galaxies further away. And as for our experience at SEAS, personally, I really enjoyed it. Just being able to do real research in a professional work environment, I think was really great. And we learned a lot from our mentors and just being able to make connections with professionals, as well as we had a lot of speakers come in and give us advice about college and our future. And I think it was a really great experience, and I'd highly recommend it to anyone who's interested.
I love the balance we had between fun activities and work. During our 2-week internship, we went to Six Flags, Dave and Buster's, the NASA Johnson Space Center in Houston, and other fun activities, along with long and exhausting working days.
I also really enjoyed this internship, and I'm very grateful that I was able to conduct research within a field that I aspire to pursue in the future. Research project. And just to conclude our presentation, I would just like to thank you for your time and for listening to us present our presentation.
Great. Please welcome our next project, the Redshift Wranglers, learning about the history of the universe.
Hi, we're the NASA SEAS Galaxy Classification Team. We are on the Redshift Wrangler subteam, and today our presentation will be on learning about the history of the universe. My name is Jackson Sula. I'm from Cleveland, Ohio.
Hi, my name is Sandra Hernandez. I'm from Miami, Florida.
And my name is Vaishnavi Koritala, and I'm from McKinney, Texas.
Starting off, we'd like to introduce the Redshift Wranglers project, a NASA citizen science initiative launched in May of 2023 by astrophysicists, PhD students, and undergraduate researchers at the Rochester Institute of Technology. The project obtains spectral data from the Subaru and Keck observatories in Hawaii, as well as the Hubble Space Telescope. Volunteer citizen scientists can then go through this published data and classify emission and absorption lines. So far, the project has made 67,299 classifications with 3,664 completed subjects out of the 5,859 total subjects in the current database being focused on. The project aims to train machine learning with the help of volunteers to identify emission and absorption lines more accurately from an object spectrum. The ultimate goal for this project is to use spectroscopy to learn more about distant galaxies, as well as improve a timeline for galactic evolution. An important concept throughout our research is redshift. You may have heard of the Doppler effect, which is when light or sound from an object, let's say an ambulance or a noisy car, increases in frequency or pitch as it moves towards the viewer and decreases in frequency or pitch as it moves away. Redshift is when light waves are shifted to longer and redder wavelengths as a galaxy or other object moves away from us. Blue shift is the exact opposite, and it is when light waves are shifted to bluer and shorter wavelengths as the object moves towards us. Doppler redshift occurs due to the expansion of the universe, and it is mathematically represented as Z, which equals the observed wavelength minus the resting wavelength divided by the resting wavelength. The resting wavelength is a value that is predetermined, and it is typically calculated in a laboratory. Our project aims to answer two main questions surrounding citizen science and its applications. The two questions being, can we determine the redshifts to distant galaxies through spectra provided by NASA's Citizen Science Project? With the given spectral data, can we refine the light travel time, or the number of years since the light was emitted from the galaxy?
When light is emitted by an object, it can be split into its component parts using a prism. This creates a fingerprint of elements called the spectrum. The data we get from the Redshift Wranglers consists of a 1D and a 2D spectrum. The 1D spectrum is a measure of brightness at different wavelengths, and the 2D spectrum breaks up the light from different galaxies into different wavelengths. Together, it can be used to find the emission lines and absorption lines from the data. The project asks amateur scientists to identify emission lines and absorption lines in the spectrum. The emission lines are peaks that stand out in the 1D plots and that are matched with bright spots in the 2D spectrum. On the other hand, absorption lines are lines that spike downwards in the 1D plot with dark gaps in the 2D spectrum. Skylines are a result of atmospheric interference, usually resulting in spikes running up and down the data, which can mess up our process. Hydrogen is one of the most common elements in the galaxy. Due to the electrons jumping to the second energy level from distant energy levels, hydrogen can present itself as multiple wavelengths. These wavelengths are defined in the Balmer series. The Balmer series helps us identify the spectral lines of the hydrogen atoms.
To begin searching for possible redshift candidates, we first searched the data for a spectrum that showed at least 3 bright emissions with minimal skylines nearby. As you can see in this image, there is 1 bright emission at the bottom and 2 bright emissions at the top. This represents a perfect candidate. Next, we noticed a pattern in the distances between bright emissions. For example, a moderately bright emission followed by an extremely bright emission usually indicates hydrogen beta and oxygen 3. As you can see in figure 1a at the top, there is a moderately bright emission followed by an extremely bright emission. This is hydrogen beta and oxygen 3. As you can see in figure 1b, however, a bright emission is followed by a dimmer one, which usually indicates hydrogen alpha and sulfur 2. Once we identified 2 emission lines, we calculated the redshift, also known as Z, for each emission using the Doppler redshift formula and the Balmer series. As you can see in this equation, Z equals the observed wavelength, which is the redshifted wavelength, minus the wavelength at rest, which is measured in a laboratory, divided by the wavelength at rest. Using the third emission line that we found, we confirmed our preliminary redshift estimate that we just calculated by dividing the third wavelength by Z plus 1. And we do this because we are no longer looking for a redshift. We already have that. We are instead checking this redshift by trying to find a wavelength at rest. We reference the calculated wavelength with an atomic spectra database and search for emissions within a few angstrom commonly found in galaxies. If there was a strong emission that matched our calculated wavelength, we could be much more confident that our redshift values were correct. And this is an image of the database that we used. By then using an accepted cosmological model, we confirm the calculated redshift by checking if the estimated light travel time matched the given light travel time. As you can see, we used a Hubble constant value of 69.7, and in this case, our redshift was 0.81. We then got a light travel time of 6.951 billion years. If these matched, we could be extremely confident that our redshift value was correct. If they did not match, however, we assume that we could not estimate the redshift of that particular spectrum with the given information.
With this process, we encounter many different challenges. First off, skylines can be easily mistaken for emission lines, which makes it hard to get the data we need. Another issue is that when determining the identities of the emissions, it is hard to distinguish it by visuals alone. After some trial and error, we noticed a pattern which made the process much smoother. In some cases, after identifying the emissions, the given light travel time differs from our calculations. This can come from a handful of errors, and usually we recalculate our data and get better results, or determine that we do not have enough information to find the redshifts.
Looking at our results, as a team, we had classified absorption and emission lines for approximately 400 objects. Out of the 400, we selected 18 objects, each with 3 or more emission lines. Above is one example of a spectrum we had chosen, and it's marked with a green check mark. The spectrum was a candidate as there are 4 clear peaks with a corresponding bright spot in the 2D spectrum. And you can see these peaks as they are highlighted in red. To the right of this image is a spectrum that was not considered, as a majority of the peaks are skylines, and there's no distinct bright spot in the 2D spectrum that would identify it as an emission. Out of the 18 objects selected, we were able to accurately calculate the redshift for 8 objects. The remaining had insufficient information for a proper calculation. This data table shows how we organized our data. Each object's emission wavelengths are determined, and right next to these wavelengths are also the wavelengths classification, whether it be hydrogen, sulfur, or oxygen. Based on the emission classification, we used the resting wavelength of the emission type and the redshift formula to calculate the redshift for each of these wavelengths. And the cosmology calculator's light travel time estimate is in the last column and is represented to two significant figures to match the given light travel time. Comparing our calculated light travel time with the values provided in the object's identification, we achieved an average percent error of 1.15%. The difference between the given and calculated data was consistently less than 0.3 billion years. Our results suggest that it is possible to estimate light travel time and calculate redshift from spectral data. The process we use to identify emissions and calculate redshift can be implemented into machine learning to create more advanced cosmological models to better understand the history of our universe.
By accurately determining the redshifts and light travel time to distant galaxies using NASA's Citizen Science Project, we helped refine cosmological machine learning and AI models. We also accomplished our goal of gaining more information from the Redshift Wrangler spectra, thus enabling the HETDEX project to learn about dark energy.
These are the references we used in our research. The first citation is for the Redshift Wranglers website. The second is the NIST Atomic Spectra database, and the last is the Cosmology Calculator. Our experience at SEAS. One of the best features of our time at SEAS was getting to work with Dr. Judith Rees and many other amazing mentors. Dr. Rees taught us a lot about our areas of research, as well as guide our thinking throughout the research process. We had so much fun and got to know Dr. Rees as the brilliant and wonderful person she is. I made so many great friends and memories at SEAS, and our team got really close over these few weeks and even took trips to Fiesta, Texas and San Antonio and the Johnson Space Center in Houston. I am extremely grateful to have such an amazing opportunity, and this experience has truly motivated me to pursue a career in space science.
I really cherish my experience here, and I've learned so much in these amazing 2 weeks. This internship has opened many doors for me, and I'm forever thankful. This was a once-in-a-lifetime experience, and I'm glad I was able to share my team's research with everyone.
My time here at NASA SEAS has easily been the favorite part of my summer thus far. I've made so many new friends. I've made inside jokes with them. I got to know my mentor really well. And I think that it did truly make me want to go into a space-based career. So thank you.
Thank you for watching our presentation.
Our next astronomy project is the Galaxy team research dark energy and the expansion of the universe.
Hey everyone, we are at NASA STEM Interns with the Galaxy Classification Team 2024, and today we'll be giving a presentation on dark energy and the expansion of the universe. I'm Lino Marrero, and I'm from Frisco, Texas.
I'm Praharshini Nuru, and I'm from Round Rock, Texas.
I'm Annie Vo, and I'm from Sacramento, California.
I'm Johanna Greer, and I'm from Memphis, Tennessee.
So our team researched dark energy, but what is that? We really don't know. It was discovered in 1998, but previous research has been done for a few decades before. The idea began to take place in the 1920s when Henrietta Swan Leavitt discovered that Cepheid stars, which are a type of variable stars, their brightness fluctuated based on distance. Combining this discovery with other research, such as the redshift discovery, led to the belief that there is some force responsible for the expansion of the universe. However, a key idea to note is that dark energy should not be confused with dark matter. Dark energy is a repulsive force, while dark matter is an attractive force. To understand dark energy, one must understand the various models of the universe. There are 4 main types of the universe timelines. The recollapsing universe theory shows that the universe will start with a big bang and end with a big crunch. The critical timeline theory shows that the universe will become stagnant after a given point. The coasting theory shows the universe growing in a linear fashion, and the accelerating theory shows the universe growing in an exponential rate. These theories are directly affected by dark energy. The decelerating universe theories, which are the first 2 theories given, these do not consider dark energy since there is no universe expansion. However, the other theories do include dark energy as part of their models since it shows that the universe is growing. Scientists recently came to the conclusion that our universe is accelerating in an exponential rate. But how do they do this? One of the main pieces of evidence given for an accelerating timeline is the supernova theory. Type 1a supernova have a constant brightness, which can be measured to calculate distance. However, when scientists tried to calculate distance using another method, using the redshift method, they noticed that the distances that they calculated were not the same. Astronomers believe that this irregularity is due to dark energy. This brings us to our research question. Can we find evidence to indicate the existence of dark energy?
All right, so let's start off with a little bit of galaxy vocab. So first of all, we have redshift, which you guys have already heard. Redshift is the amount of a galaxy's light that is stretched towards the red end of the spectrum, and it's due to the expansion of the universe. And essentially, we just use it to measure how fast a galaxy is moving away from us. Next off, we have right ascension, RA, and declination, DEC. And like Earth's surface coordinates, but only for objects in the sky, like stars and galaxies. RA is like longitude, measuring east to west position in the sky along the celestial equator, and DEC is like latitude, measuring from north to south position in the sky relative to the celestial equator. Finally, the last vocab word we have is confidence level. It's rated on a scale from 0 to 1, and it shows us how confident the HECDEX data analyzers are that a galaxy is truly a galaxy and not noise. So the closer to 1, the more likely it's a galaxy.
So we discussed right ascension and declination a lot throughout our project. So we decided that it's a good idea to have a visual representation. So as you can see, the declination and right ascension are used to indicate where an object is relative to the celestial poles. The sphere that is seen surrounding the Earth is the celestial sphere.
Next, we gather information from the HEDEX. The HEDEX is the Hobby Eberly Telescope Dark Energy Experiment at McDonald Observatory. It uses a set of spectrographs to map the three-dimensional positions over 1 million galaxies. It also aims to create the largest map of the early universe. That map is able to tell us the rate at which the universe expands at specific points in history, and that highlights the place dark energy has in the history of the universe and its influence on objects. We also use Dark Energy Explorers, which is a citizen science project utilizing data from the HEDEX telescope. We use volunteer input to distinguish classifications between galaxies, black holes, and noise. The objects are 9 to 11 billion light years away, and it helps us to extend our understanding about dark energy and its contribution to the expansion of the universe.
When classifying our data, there were 4 different types of data that we looked at. First, we looked at fiber images. Each of the colored boxes seen on the left shows one type of fiber image. Then we looked at spectrographs, which can be used to find redshift and distance. We then looked at imaging postage stamps, which show the location of atoms of the given data. Lastly, we looked at line flux maps, which show the absorption and emission lines, which can be used to find a lot of data, including temperature and density of the objects that we were looking at.
All right, and now into our hypothesis, which is that we can use HEDEX data to find galaxy clusters in the early universe at 9 to 11 billion light years away.
But for a galaxy to classify as a real source, we need to look at data. So for our first set of data collection, we look at spectrographs. So these blue dots are actual data points and their ranges, and the spikes are their emission lines. And when they lines up with the black line there, then that means it's good data, and that means it's an indication of no noise and no skyline. And it's a good line of fit because it has to be on the black line. Another thing about these spectrographs is that black holes can be identified easily as they have a longer wavelength and they're easier to distinguish. But moving on, if the plots and the dots fit, then we will analyze the line flux map. So on the left, we have a bright yellow dot in that red square, which is a good indication that that's a good signal. And on the right, we have no distinction between anything, which means that is just a sea of noise and it can just be classified that way and thrown out. And then we move on to talking about the fiber images. In these images with the colored borders, we see a distinct black dots on the left side in each image that help indicate a galaxy. And that will help distinguish between a galaxy and just noise. So the gray is noise and the black is signal. Each signal is a composition of several spectra, and the rectangle show individual fiber spectra. The black box is a combination of all colored boxes, and as a result, if we see a strong signal in each of the colored boxes, then we can more confidently say that it's a galaxy. If it's only in one box, then that means it's just noise. Streaks also indicate bad data and should be thrown out. With this data, we can also identify black holes. So you can see that it's not a galaxy and it's not noise, but it's a black hole. Those are very rare, but it's also not important to the Zooniverse project as we're looking for galaxies.
So why clusters? What makes them significant and why are they important to us? Well, dark energy is the theoretical idea that if it exists, causes the universe to expand at an accelerating rate. If a cluster is found, then the belief that dark energy exists can, if we analyze the way clusters and the galaxies looked then versus how they do now, we can see if they spread apart, which would then mean that an outside force had to have pushed them away from each other. That outside force could be dark energy, since if we find the galaxy spread out, it can indicate the universe is expanding at an accelerating rate, which is done effectively by a dark energy. But our goal is to plot out the locations of galaxies so we can find the clumping of galaxies indicating galaxy clusters. These galaxies are from the earlier years of the universe, existing anywhere from 9 billion to 11 billion light years away. Analyzing our data sets. We looked at more than 130,000 classified galaxies from the public data release of HETDEX through the Dark Energy Explorer Citizen Project. The first steps we took to manage this much data was to narrow our declination angle range to anywhere between 49 and 54 degrees, and limit any results we got to a confidence level of 0.75 to make sure we were being accurate and reliable.
Okay, and now we're going to go about our cluster collection. After narrowing down our data sets, we are ready to start identifying clusters by eye. We visualize the data in a 2D Cartesian coordinate plane by dividing the galaxies by small declination ranges and use the redshift cosine right ascension and redshift sine right ascension equations to determine the x and y coordinates for each galaxy and plot them on graphs. This allowed us to determine if there were identical galaxy clusters by eye. So right here, we have one example of declination range 49 to 50, and in the red box, you can kind of see some concentrated clumping of galaxies. So we decided to check it out. And after we identified potential clusters, we had to narrow down the graph for the selected points and replot our points on a DEC versus RA graph and check the distance to ensure they're actually close enough to be a galaxy. So while on the bigger graph in the top right, you can see that it does look like they're clumped together. On the lower graph in the bottom left, DEC versus RA, you can actually see the points are pretty spread out, which is a strong indication that this is not a cluster. However, we were able to locate two more potential clusters based on clumping by eye in the declination range of 53 to 54, labeled below 1 and 2. And in our first one, after we narrowed down the data, or narrowed down the graph to a smaller DEC versus RA range, and plotted it on the graph you can see in the bottom left, we can see that they're actually packed pretty closely together. And this is likely a cluster candidate with around 16 galaxies. And again, on the top right, you can see where our original clumping was. And this was potential galaxy cluster number 2. And again, in the top right, we looked again and good indication of clumping. We go down, look at the DEC versus RA graph, and yes, it definitely looks like it could be a cluster candidate with 12 galaxies.
So what are the results? We learned to classify galaxies. We helped sort data for the next release. We used previous classified galaxies to discover clusters in the early universe. We found that new clusters were 10.5 gigalight years away, and this all helped us to better understand the universe's expansion.
How can we sum up our NASA STEM experience? We all had an amazing time, and it's very hard to sum it up into short sentences, but we tried. For me, it was a great opportunity to learn a lot, meet tons of great people that I will be friends with for life.
For me, NASA STEM's internship has been an amazing opportunity to meet new people, try new things, and learn a ton.
Personally, this program allowed for a lot of growth and personal connections to grow, all while discovering new things.
This NASA internship was an amazing opportunity, and I felt like it opened the door for many more opportunities in the future. I met some amazing people and I learned a lot of great things, and I'm so excited to be part of this trip.
Okay, and here's our references. And yeah, thank you guys so much for tuning in. And also, we'd like to say an additional thank you from all of us at the Galaxy classification team. to NASA, NASA SEAS, CSR, Dr. Judith Reese, our mentor, thank you very much. And additionally, Miss Margaret Baggio, Miss Tomlin, and Miss Selena Miller. We really appreciate you guys a ton. So thank you so much for this opportunity.
Great job. We invite all three of the Galaxy classification teams to turn on their cameras and unmute their mics. We have several questions for the teams. For the Redshift project, is there a defined rate at which the maximum distance for identifying redshift is decreased due to the expansion of the universe?
I can answer this question.
For the Redshift Wrangler team.
Can you hear me?
Barely.
Okay. So our research didn't really focus on that, but there is a way to find the rate. It would take into account the Hubble constant, other parameters like dark energy and the curvature of the universe, as well as redshift, which was what we mainly focused on in our research. But yeah, I would say there is a way to model that, but we just didn't really focus on it much in our research.
Perfect. Team number one, what was your biggest challenge in navigating your project?
So I would say that our biggest challenge in our project was classifying the different CFIDs because, as we mentioned earlier in the presentation, there were different types of CFIDs. And if we had spectral data from Gaia, then we would have been able to better classify them. And that would have improved the accuracy of our data.
Team number two, how did you choose the 18 objects as your sample?
I can answer that one. So for the 18, we specifically looked for galaxies that had at least 3 very bright emission lines. And from then we calculated our data from those. Usually if they had only 2 bright emission lines, our data would be very, very off from what was given to us.
Team number three, what impact has this experience had on your future goals?
For me, definitely this experience has led to me become more interested in astrophysics and potentially as a form of study in college for me. So it was very useful to me.
Great. And for team number one, did you have any prior knowledge before starting your research?
So I actually didn't have too much knowledge about the field of astronomy prior to this internship, so I was learning a lot of new information throughout the progression of our project. However, the ESS lesson modules and the assignments that were assigned by our mentor, Dr. Reese, were very useful, and they were a great introduction to the field of astronomy.
Great. Team number three, of fiber images, spectral graph, postage stamp, and others, did you have a preference of a method?
I'll take this one, but I think our preference of method didn't really classify, like we didn't prioritize one over the other, but we did use each and every one to help indicate the presence of a galaxy, which was very important because they all coincide with each other. We couldn't choose one to be more important than the other because if the fiber images didn't line up, but the spectral graph did, then that means it's not reliable data. So I would say that all of it was important.
Great. Team number two, were there any other factors to consider when differentiating the emission lines and skylines? Fascinating research.
So usually when there was a skyline, there was a really bright white line below it. But usually when there was a mission, it was slightly broader and a little bit more dim. So we could usually pick out whether it was a skyline based on that. But if it wasn't, you could look for a dip and then a spike following that. And that usually told us.
Perfect. Well, you all did an excellent job. Congratulations on your research. Our next SEES project is from the Architecting AI for Human Space Travel team led by mentor Bridget Kimsey. She is of the Lenape and Celtic descent. She has been working inside global indigenous methods and Western scientific methods for over 30 years in the areas of healthcare, research, writing, policy, and security. She is currently a PhD student in artificial intelligence. She serves as a solar system ambassador for NASA JPL and a researcher on the exoplanet and study of the impact of COVID-19 on remote native tribes in North America. She teaches at the University of Vermont and has her own primary and secondary research and writing components. So please join me in welcoming the Architecting Artificial Intelligence team.
Welcome to our NASA SEAS team project, Architecting Artificial Intelligence. My name is Bridget Kimsey, and I am currently working on my PhD in AI, and am also a solar system ambassador for NASA JPL. Our team of 11th grade interns will get started here in just a moment. Our topic is looking at current and suspected problems in AI development and some options, including for deep space travel. The study rests on a premise that the structure of biological life forms older than the human animal, and many other forms of structure in our universe, solar system, physics, development of other ecosystems, how these structures create, store data, problem solve, create complex structures could be very important in how the modern dominant culture creates AI safely, healthfully, and efficiently. The study is looking at how can AI be created for a particular need by following these playbooks. So we begin on our journey here with Drake Sage taking the floor now.
Hello, my name is Drake Sage and I'm a rising senior interested in aerospace engineering. Today I'll explore how understanding bee communication can enhance the capabilities of collaborative combat aircraft, or CCAs, which are AI-powered wingmen that are currently under development in military operations. First, let's look at various uses of CCAs in military. CCAs can gather critical intelligence on enemy movements and terrain, transport essential supplies to the battlefield, and provide offense in the air. CCAs are meant to work alongside human aircraft and assist them in missions. However, this technology faces a significant threat in the military field. They rely on radio waves for communication, making them susceptible to electronic jamming by adversaries, jeopardizing mission success and the safety of personnel. Bees have a very unique habit called the waggle dance. It involves specific movements and vibrations to convey distance and direction of food. How can this be applied to AI drones? This can be done using similar physical signaling methods. I'm proposing that drones use light signals, such as infrared, to communicate with each other. Sensors on the drones would pick up these signals, and AI can interpret them. This method would be unable to be electronically jammed, making it highly reliable in combat situations. Now, let's consider how AI makes bee-inspired communication advantageous for drones. AI allows drones to use machine learning for decision-making and interpreting this communication, reducing the amount of logic system required in the drone's payload, and therefore allowing for other weapons and technology to be carried instead. AI can develop different signals, such as various intervals of flashes before operation, enhancing adaptability to different scenarios. For example, if communication to home base is jammed, AI drones can still communicate and finish the mission while also returning home safely. Also, if the manned aircraft were to be destroyed, drones would still be able to function, preventing the risk of enemies only targeting the human in dogfights. This improves the potential of CCAs, reducing the risk to human pilots and ensuring higher reliability and survivability, overall leading to a higher mission success rate. In summary, modeling bees communication methods can eliminate major threat to drone technology, ensuring that they become reliable and effective in modern warfare. This approach not only addresses current communication vulnerabilities, but also highlights the potential of AI in future military operations. Thank you.
Thank you, Drake, so much. These are Drake's sources. Moving on to Trey. Trey 9, you have the floor.
My name's Trey 9. I'm also interested in aerospace engineering. However, I focused on how we could use AI to produce rockets in a very timely manner. While looking into this topic, I figured out AI could be trained to mimic ant colonies, which already are massive marvels of productivity and coordination. Rocketry needs that productivity if we are to get to other places on in the solar system and stay there. Furthermore, AI trained with ants could bring up the rate at which we produce rockets to this level. we're to a level where we could mass produce them. Ant colonies are, like I said, very efficient. They work together seamlessly to build massive, huge ant mounds and other things. And if we could imagine if we could replicate this in rocket production. Take these here's an image of the Artemis core stage. The first one took years to build, and an AI inspired by ants could have shortened this production time significantly, and could get to our exploration, and we could get to our exploration goes faster if that time was shortened. In the second core stage, which just rolled out a few days ago from the production site, was quicker to build, of course, but AI trained with these ant principles could accelerate that process even faster. Massive robotic assembly lines, changing needs with precision of ants building their colonies. Picture like maintenance systems that predict issues before they even happen, keeping rockets ready for when we need to go with them. Overall, AI could help improve the rate at which NASA and even private industry could produce rockets.
Next up is Austin Bruce.
Hi, I'm Austin Bruce, and I chose to research the consequences that come from the introduction of quantum computing as it grows into a monetized field, and what the addition of AI will entail on the world stage. The widespread research being conducted on quantum computing is similar to Robert Oppenheimer and the nuclear bomb. The ability to split the atom was a physics phenom not thought to be possible, alike the ability to use photons at a microscopic level in order to compute information. But to be able to compute at such a minuscule level comes with a set of challenges. First, to house the qubits. Absolute zero must be maintained. Secondly, the structure and housings of the photons acting as transistors are deeply complex. Third, quantum parallelism is unworldly abstruse, due in part to the algorithms that follow quantum parallelism. Developments from companies such as IBM, Google, Intel, Microsoft, these companies have begun to burgeon, which pins the question of pros and cons that follow quantum computing. Now, what is quantum computing, and what is it founded upon? Quantum computing is a form of computing which uses microscopic photons in replacement of the average transistors found in a normal computer or supercomputer. Quantum computing computes information significantly faster than the strongest supercomputer. Each month, it's changing, and quantum computers are only gaining speed, but Google's quantum computer is at this point 241 million times faster than the world's fastest supercomputer, due to its amount of qubits. An example of how problem solving differentiates between supercomputers and quantum computers is a maze. A supercomputer will solve a large-scale complex maze by scanning each individual pathway, failing and then restarting until it picks the correct path. On the other hand, a quantum computer will scan every possible path at once without failure and find the correct pathway in order to solve the maze. Quantum computers can be used to solve high-level math problems and puzzles because of its nature. The pros and cons and cause and effects of quantum computing. Pros. Quantum computing speeds up processes 9,000 times faster than normal supercomputer for every 200 qubits. So, like better quantum computers, the more advanced they have more bits, and it just multiplies. But when expanded, it could reach millions of times faster. It could give more availability to internet to less fortunate parts of the world. Cons. It could lead to widespread data theft. It could be held behind a paywall and used with negative connotation. It could lead to tension, which could cause nuclear level threats. To conclude, quantum computing can lead to a negative and positive effects of the world stage. Will it be used for good or bad? Who knows? Here's my sources.
Thank you, Austin. All right. Next up is Caleb. Caleb Matthias.
So my name is Caleb Matthias, and I really like biology. So my topic was the use of AI in spaceflight and space travel. So as human space missions begin to look farther and farther away from Earth in the coming decades and centuries, one of the key questions is medicine, healthcare, and the availability of that in space for astronauts. So as the distance between Earth and spacecraft increases, so do travel times of signals. So communication between mission control flight surgeons and the astronauts gets reduced heavily. And in space, there is observation of health, like in the Kelly twin experiment from the ISS, from other things like the lifetime surveillance of astronaut health, but a lot of that's in lower Earth orbits. There's not too much for deep space. And this project aims to use biology like natural phenomena as problem solving as a point of inspiration to architect and implement AI in a way that would help. So self-assembly is the first idea, which is the idea if the cohesive parts of a structure come together without necessary human intervention. Self-assembly can be found in nature at the fundamental level of life in cells. So cell division, multiplication through mitosis, and other processes happen billions of times in the human body every day, just on the base sequences of DNA and replication of already existing organelles and other structures. Self-assembly addresses the issue of AI as a newly emerging source of information, which is able to process and make inferences based on given data sets. In this case, those data sets would be the medical records available as a backbone, and then which it could go off of. And it's more than the sum of its parts. In this case, with the new function to be able to crunch data, make interpretations for flight search and use in deep space in relatively short time periods. And then we can look at that like these moths. So peppered moths adapted from the white speckled colors to a darker color based on soot from the industrial evolution from a changing environment. In the same way, AI could hopefully adapt to different environments like deep space. AI could also function as like a relative hive mind. So hive mind intelligence, especially in the context of bees or wasps, refers to a notion where hundreds of individuals in a species express their preferences, and this continues until a decision is made that matches numerous factors, which is often the most optimal decision. And medical AI would mirror this, searching records for the best matches as well as making the best inferences based on data available. And in this case, AI could function at a massive hive mind since it's able to store information at a function rate much higher than regular human capacity. So while flight surgeons do preside a very necessary role in spaceflight, being able to reference new information and health signals and take away from old data sets at a speed much faster than humanly possible is where AI can really help taking a brunt of that like mechanical load away. Thank you.
Thank you, Caleb. We're moving on into Diego Rivera's.
Hello, everyone. My name is Diego Rivera. I am going to my senior year now in Puerto Rico in a school named Colegio Rosabel. My main interest with this project and this theme and the way I went about it was that, since being a kid, I've always been a very creative person. Whatever needed my creativity, I would give it. I would always go out of my way to, help someone who is stuck, writer's block per se, but I mostly wanted to focus on how AI could improve the way that we view rocket design. Let's say, you're working and you need a rocket design by said time. Obviously, it's not going to be all done by that time because things happen. Delays are inevitable. But what I wanted to do with this was propose an AI tool that could be implemented into any 3D modeling engine or creating a new engine that could help us visualize a new rocket or inform us on what rockets in the past have been doing and how we can improve by certain metrics like fuel tank sizes, materials, hull sizes, and shape them into more or less what we want for now. And in that, we're going to be mixing a lot of old and new designs, just trying to see what sticks and what doesn't. But yeah, the AI part of this has been very intuitive from because I did my own research of AI, and AI is sometimes it's a little bit difficult, but most times it's coherent, and it could be a great tool moving forward for humanity, that we can definitely rely on, not overuse, but rely on. And in that, it could get us further than we already are in a shorter time. Thank you so much.
And we'll go into Colton's work. So Colton Boyd, you are up next.
My name is Colton Boyd. I'm from Kentucky. I'm interested in natural sciences as well as physics and philosophy. And my topic is going to be almost a warning for AI in the future, and it's going to be about AI misalignment and deviance. First off, there's a lot of good things that AI can provide for us. Right now, it's doing so many things in terms of communication, manufacturing, healthcare, and all of those sectors. They're really utilized to the best of their ability. But one thing that we need to consider going forward is misalignment and deviance. Misalignment is the idea that AI will perform a task that it's given, but not operating under human values, ideas, and morals. An example would be if you were to give an AI the task of creating paper clips most effectively as it can. Given enough time and resources, it's very possible that the AI would end up wiping out the human race in order to make room for factories to make more paper clips, right? So it's a very extreme possibility, but it's there. And there are many other minor misalignments that could take place that could really have a big effect on whatever sector it's in. And kind of on the same note, deviance is whenever AI pulls from biased data sets, as well as data sets that we don't want it to use, and it forms ideas and comes to conclusions based on those data sets. We can see this a lot right now, where there are a lot of AIs used for communication and general knowledge, similar to ChatGPT, where they're pulling from biased data sources just because that's what it's been presented with, right? So you can almost kind of look at both of these things as how evolution plays out in microbiology, right? Whatever the microbe or organism is presented with in its environment, it's going to immediately adapt from the data it's given based on what it's seeing and how its environment is affecting it, right? So when AI is progressing, it's really on us to determine what the AI is seeing in terms of the data it's pulling in and how it's affecting us. And kind of on that, I think that it may get to the note where a lot of people are thinking, oh no, if we don't do something right, if we program it wrong, AI is going to become the Terminator, right? No, this is really just about us forming a good bond with the AI, right? Not kind of in the actual emotional sense, but how we're presenting data to it, right? For example, especially in physics modeling, if you were to give the AI a set data set and have it model something, right? If you were to forget just one little thing, a law or just a way about how momentum works or something like that, you would get a completely different result from what you wanted. Not exactly what we're looking for, right? So going forward, it's really our responsibility to make sure that AI is evolving at a regulated level that's helping us and operating under our values and morals. Thank you.
Great, thank you, Colton. All right, next up is Chidabam Umazon, and he's going to be talking about using fish characteristics for spacecrafts.
All right. Hello, everyone. My name is Chidabam, and today I would like to discuss my topic about how fish-inspired AI and robotics can revolutionize space exploration. By integrating the advanced behavioral systems and physical characteristics of fish into AI-driven robotics, we can significantly enhance mission efficiency and adaptability. Firstly, let's talk about movement and maneuverability. Fish like tuna exhibit dynamic movement, allowing them to navigate through water with incredible precision and efficiency. This characteristic can inspire the design of agile robotic systems for spacecrafts, ensuring precise navigation in the challenging environments of space. Studies have shown that biologically inspired propulsion systems originally developed for underwater vehicles can be adapted for space, offering improved maneuverability and energy efficiency. Secondly, we can consider the concept of shape-shifting holes. Just as fish can alter their body's shapes to move more efficiently, spacecrafts can be designed with flexible holes that morph to optimize aerodynamics during different mission phases. AI systems can dynamically adjust these holes based on real-time data, enhancing performance and fuel efficiency. Next, we look at efficient propulsion systems. The flowing movements of fish tails inspire propulsion mechanisms that provide both efficient thrust and maneuverability. AI control systems can regulate these propulsion mechanisms, ensuring precise navigation and optimal energy use. Another fascinating application that fish have is swarm coordination. Fish exhibit remarkable schooling behavior where they move in a coordinated manner, sharing information and adjusting their positions in real time. AI algorithms mimicking this behavior can manage fleets of autonomous spacecrafts, enabling efficient communication and coordinated movements for tasks like data collection and space debris management. Additionally, Fish possess advanced sensory systems, such as lateral line, which detects changes in water pressure and vibration. This can inspire the development of advanced sensory systems in spacecraft, improving navigation and obstacle avoidance. In summary, the integration of fish-inspired AI and robotics into space exploration offers a transformative approach by mimicking the efficient movement, adaptable hulls, and coordinated movements and advanced sensory systems of fish. We can create spacecrafts that are more efficient, adaptable, and are capable of handling changes of space more effectively. Thank you.
Thank you so much. Really fascinating, all of you. These are your sources. Here we are at the end. So we all want to say thank you. So
Thank you, C's.
yes,
Thank
thank
you,
you,
C's.
C's. Thank you,
Thank you,
NASA.
C's.
Thank you. Thank you.
So we invite the students on the Architecting AI for Human Space Travel team to turn on their cameras and unmute their mics. We have several questions for the students. What were the most challenging issues you faced while researching AI?
I can answer that. So I think the most challenging part about researching AI is that there's so many things that could be done with it, but also when it comes to recently, AI has developed like a pretty bad stigma. So I think having to research it and find the ways that it could be used while also making sure that it is used properly and not in a dangerous manner, while like making sure we can give it or like renew its name and give it a better stigma than what it has originally achieved was the most challenging part.
This question.
Yeah, researching it as a clean state. Sorry.
That's okay. I have a question for you, Austin. Regarding quantum computing, do you think quantum computing could be a cost-effective alternative to current computing if widely implemented?
I do think it could actually be. Once housing is figured out and companies have final products, I think just like nuclear energy, I think like nuclear energy, if used properly, could be much more efficient and especially for US as a nation. And I think quantum computing could do the same when it comes to that.
Misalignment is an interesting topic. Would there be a way to mitigate this?
I can take this one. So currently, the best way we have to mitigate this is to implement laws that the AI has to abide by that kind of uphold human morals. An example would be Asimov's 3 laws, which kind of just state that the AI cannot come to harm a human in any way. It cannot bring harm to any group of interest that it thinks is harmful to humans unless given authorized, and it cannot self-implode without breaking the first 2 laws. And there's a lot of other things that go into it with just specifically how we programmed it and just making sure there's nothing wrong with it. But as of now, that's the best way that we know how to stop it.
So the next question is, in your opinion, is AI usage advancing too quickly without enough data, guidelines, support? Anyone want to take that challenge on?
Yeah, I'll take it. I'll take it. I think it's mainly just because it's so new. Like it's been around for a good amount of time toward now it's developed and now it's multiplying at rates where it's not only becoming more popularized, but it's becoming more used. Like people even up to like real estate are using it to like list properties, you know. And to answer the second part of it, I think it could be used negatively and positively. And um hmm. What was the second part of the question exactly? Oh, great, you can
I
finish
can
that.
expand on that. I think just following guidelines such as one of the ones that I know of is the DoD's responsible AI strategy. Following different guidelines like that, and of course they're going to have to be developed as AI gets bigger and the technology improves. But adhering to those guidelines will make sure it's still safe, even though it's expanding rapidly, and then we can use it to its full potential.
Awesome. Well, you all did an excellent job and I learned a lot. Thank you for joining us today. The Air Quality Initiative teams are led by Yitong Jang, Sarah Mirzwiak, Juthi Mitra, and Grant Wilson. They are all research assistants with the NASA Globe Mission Earth Project. We will have 5 projects presenting, followed by Q&A.
Hi, this is our project on estimating ground level ozone.
So ground level ozone is of particular interest to us because of the negative health and environmental impacts it poses. It's linked to respiratory, metabolic, and reproductive issues and is known to cause considerable damage to vegetation. So one way we measure ground level ozone is through ground monitoring stations, which is used a lot by governmental agencies. However, they are expensive to set up and they're lacking presence in rural and underdeveloped areas. So in developing regions, actually, there's an inadequate amount of ground monitoring stations. So therefore, there's a lack of comprehensive air quality data in those regions.
On the flip side, you have satellite data, which has near total spatial coverage, but it only measures vertical column density, or VCD. This includes both helpful stratospheric ozone and harmful tropospheric ozone. So while it's certainly helpful, it's definitely not an accurate proxy for ground level ozone. So in order to get around this, we aim to use machine learning methods to estimate ground level ozone using the VCD we just mentioned, as well as auxiliary variables like meteorological, chemical, and land use data, all of which affect ozone formation. For the machine learning methods, we use multiple linear regression and random forest regression.
So more on our input variables. For our meteorological variables, we selected solar radiation, maximum temperature and precipitation, and vapor pressure as our input variables. And then for our land use variables, we decided to select NDVI. And then for our VCD data, we chose precursors of ground level ozone, which include nitrogen dioxide, formaldehyde, and carbon monoxide. And we also included the column of ozone, total ozone, with stratospheric and tropospheric ozone itself. So here is our input variables as time series, and then this is their spatial distribution.
So this is a workflow diagram of how our project worked. We started with input data sets from Google Earth Engine from a variety of sources, and we then consolidated them into one single table. And this was done in a way where you can imagine each row in the table as a stack of pixels over a ground level measurement, as you can see from the X's in the bottom left. From here, once we had the data set, we evaluated the accuracy of different models using a trend test split and accuracy metrics. Our study area was in Southern California. We chose these 8 locations, and on the right is the same data in the tabular format. For our results for linear regression, we achieved a pretty low mean absolute error of 11.4 micrograms per cubic meter and an RMSE of 14.3 micrograms per cubic meter. Our random forest regressor did significantly better with a mean absolute error of just 9.78 micrograms per cubic meter and an RMSE of around 12.3. Our R-squared value, which determines the correlation of input to output, was around 0.46. However, the study had its limitations that we want to acknowledge, mainly that the study area was in Southern California, making it harder to evaluate the impact of things like precipitation and humidity, because there simply isn't a lot of rain in Southern California. Our training data set was substantial, around 5,000 points, but it was still relatively small, and we'd need it to be bigger to try more complex machine learning approaches. We also had very little time to put this project together, and in the future, we're considering incorporating more variables.
So Purva and I would like to give a big thank you to NASA SEAS, especially the entire Air Quality Initiative team. And this was all made possible by the amazing mentorship, especially Juthi, Dr. Jan, and Dr. C. Thank you so much for your invaluable time and mentorship.
So despite all of this wonderful support, we did run into some challenges, mainly downloading and visualizing relevant geospatial data, especially without any formal GIS training. We ended up turning to Google Earth Engine for this reason. And another issue that we encountered a little bit earlier on was just understanding the problem space as a whole. However, we do want to thank NASA SEAS for all the skills that we came away with. For me, that mainly means diving more into geospatial data analytics, and I'm eager to continue looking for ways to do impactful research in the future.
So for me, coming from a chemistry background, during the background reading, I was able to expand my knowledge of atmospheric chemistry, and I'm eager to further my knowledge in environmental and atmospheric chemistry.
Thank you so much.
Hi, my name is Aracelis Dominico Jesus Tolaza, and I'm from Piaget Bilingual Academy of Manatee. And today we're going to be exploring the correlation between air and water quality.
The root problem. Both drinking water quality and air quality have significant effects on human health. Literature also supports that there is a connection between air quality and water quality. We believe that as PM 2.5 and temperature in the air increase, the quality of the water through pH, dissolved oxygen, and temperature will decrease.
Our defining variables for this project were PM 2.5, air temperature, pH, dissolved oxygen, and water temperature. To collect the air data, we use a continuous monitoring of PM 2.5 and air temperature using Purple L and IQ air sensors. To collect the water data, we use a continuous monitoring of dissolved oxygen, pH, and water temperature at 2 sites using USGS. The sites are near Houston and Bayamon. We recorded the data orally over the first week of July 2024.
Here's an overview of the Houston data site. The water quality tracking and air quality tracking are roughly 2.8 miles away. Seeing the correlation between temperature and water quality traits, there is a positive correlation. Interestingly, the correlation between the air temperature and the dissolved oxygen content in the water is a stronger correlation than between the water temperature and the dissolved oxygen in the water. Looking at the correlation between PM 2.5 and water quality in Houston, there doesn't seem to be a significant correlation.
Here's an overview of the site from the water and air sensor that are 2.2 miles and 6 miles away from the site. And for the PM 2.5, there seems to be a strong correlation between the PM 2.5 and the water temperature and the pH, but there's a low correlation with the dissolved oxygen. This is a site for the water quality. The air temperature seems to have a high correlation with the pH and also with the water temperature, but again, with the dissolved oxygen, the correlation is really low compared to the others.
Looking at the two sites, the PM 2.5 seemed to have a stronger correlation to the pH and dissolved oxygen in Puerto Rico. However, in Houston, it was the air temperature that seemed to have a stronger correlation. Hi, my name is Jennifer Raymond, and I'm from Richardson High School.
The analysis of our data, we have the PM 2.5 versus the water temperature, as PM 2.5 reduces the dissolved oxygen in the water, which as a side effect causes the water temperature to increase, and the higher the water temperature, the lower the dissolved oxygen. We have the PM 2.5 versus dissolved oxygen. The PM 2.5 increases the turbidity in the water. When that happens, there's not enough sunlight that can reach onto the underwater plants, and the less sunlight, the less photosynthesis, and the less dissolved oxygen in the water. The PM 2.5 and the water pH, when large amount of PM 2.5 in the atmosphere can cause acid rain, and when that acid rain comes in contact with the water, it lowers the pH of the water, and as a result of that, the water obtains acidic properties. and the air temperature versus the dissolved oxygen. As mentioned before, when water temperature increases, the dissolved oxygen decreases. So when the air temperature increases, the water temperature, as a result, the levels of dissolved oxygen in the water decreases.
During our internship, we had many challenges, but we also had highlights. Some of our challenges were working virtually in different time zones, learning Excel, and understanding graphing relationships. But some of our highlights was being able to download these large data sets, creating correlational graphs, and getting new understandings of the interactions between air and water in different locations. Over these past weeks, I feel a lot of growth from this internship. I also know that in the future, I want to continue exploring research, as that was something I really enjoyed.
This week, I was able to recognize a significant improvement in my knowledge and personal skills obtained over this internship. I acknowledge how much I really enjoy doing research and how teamwork is one of the best tools for science.
Thank you.
Thank you.
Hello everyone, my name is Josh Chandra from the Austin, Texas area.
Hi there, I'm Mina Chan. I'm from Castro Valley, California.
And we're investigating the effect of green infrastructure area on PM 2.5 concentrations and its relationship to respiratory illness. So as an introduction to our project, what is even PM 2.5? Also considered fine particulate matter that is less than 2.5 microns in diameter. This basically means that it's small enough to get into the human bloodstream, which is not good at all. There's literature to support the causational relationship between air quality and green infrastructure, and also a causational relationship between air quality and respiratory illness. We have supporting literature for both of these findings. This shows that as air quality decreases, the amount of respiratory illness increases. Furthermore, there is supporting literature to support that as air quality increases, there seems to be an increase in open green spaces. So how are we going to define green infrastructure for this project? There's so many ways to define it, but for our project specifically, we're going to focus on two things. We're going to focus on the surface area coverage of number 1, green open spaces, and number 2, water bodies within county borders. What are we investigating? Our research question is, how does the ratio of open green space to total space in a certain county correlate with the air quality and respiratory illness prevalence within those areas? So why are we choosing this topic? So you can see through this diagram that there are 3 main parts to our project, but research is poorly understood between the gap between respiratory illness and green infrastructure, and we aim to fill that gap with this project.
Our 2 California study groups are the San Francisco County group, which is San Francisco and the 8 counties surrounding San Francisco County, as well as Los Angeles County and the 5 counties surrounding Los Angeles. We acquired the annual population of all of our counties, current open space data, and the number of cases of COPD and community-acquired pneumonia. Looking at the graphs, we're able to see that there is a positive association between PM 2.5 in micrograms per cubic meter and the number of cases of COPD and community-acquired pneumonia. In some of the counties, there are separations between PM 2.5 concentrations and our respiratory data, but since it's occurring over multiple county graphs, we can assume that this is due to outside factors. Once we add in green space data, we can see that there's a correlation between the percentage of green space and where the rest of our data lies. The graphs show that a certain area needs at least 5% green space in order to keep their PM 2.5 concentrations and the number of cases of respiratory illness that occur low. Our research also concludes that in terms of our 2 county groups, the LA County group has low green space percentages that are mostly less than 5%. SF County group has green space percentages that range from above 2% to below 20%. The Los Angeles County group has lower rankings in terms of PM 2.5, COPD, and pneumonia data. It actually indicates that they have a high PM 2.5 concentration as well as high respiratory cases. Most of the challenges associated with this research project were in terms of our time management, since it takes time to acquire access to information and collect data, as well as rework any elements that need to be redone. The best thing about this internship was that it allowed us to collaborate with people who we might not have collaborated with otherwise, and work with people who have similar interests to ourselves. It was nice having the accountability of deadlines since it encouraged us to accomplish the work that we needed to get done.
We also found out that we had to redo and rework many elements of our project numerous times, as we were really trying to optimize what we wanted to get out of the project and what our goals for our research were. Although we really did like the collaboration and the deadline accountability from both of us. Now on to the reflections from both Mina and I.
I found out that I enjoyed the data collecting within the research process. This internship allowed me to see what I could get done with limited time and resources, and that's encouragement to continue researching in the future.
I've noticed that the perspective I've gained from Earthscience, using that to benefit public health, was a really interesting perspective that I could only get in this internship. In the future, we can use different analysis to confirm the causational relationship between air quality and green infrastructure, and air quality in respiratory areas. Also, we would like to present and eventually make a publication for AGU 24. Thank you to everyone who supported us along the way, especially our mentors. We look forward to continue to contribute to the scientific community.
Hi everyone, my name is Isha Gupta.
My name is Magna.
And our research project is called Air Quality Correlation to Socioeconomic Status in New York City.
We chose this topic because we saw an article that stated that greater exposure to environmental hazards is one driver of health disparities found among communities of racial or ethnic minorities and those of low socioeconomic status. Isha and I wanted to make more people aware about this gap using the data that we found.
Our research is based around one central question. How does air quality compare between individuals across different demographic groups based on race and ethnicity and median household income in New York City? One of our hypotheses going into our research was that individuals who live in areas with lower median incomes will be exposed to more PM2.5 emissions and therefore lower air quality.
Our other hypothesis is about the correlation between race and air quality. We hypothesize that white individuals will face less PM2.5 emissions than those from a colored or minority background.
While exploring the literature on the subject, we saw three main points. Research shows that poor air quality has been linked to health problems prevalent in low-income and minority communities. And two studies prove that areas with higher concentrations of PM2.5 often have a higher percentage of minority and low-income residents because these residents are often situated near major roadways and industrial zones.
The data for race and ethnicity and median household income was collected from the U.S. Census Bureau. The PM2.5 data was collected from Washington State University. Our PM2.5 data is on a scale of 6.3 to 9.6 micrograms per cubic meter of air. The median household income can range from below $20,000 to above $150,000. The race and ethnicity data shows the percent of colored people for each census tract. Here we made a map that shows New York City's 5 boroughs in their counties. When looking at the scatter plot, there doesn't seem to be much disparity or gap between the low-income or high-income communities in each county or borough. But by using the trendline feature, which shows the pattern or trend for each graph, we can see that for each borough, the trendline declines as the income increases.
Here we have two maps, the one on the left showing percentage of minority groups and the map on the right showing the amount of PM2.5 emissions. When looking at these maps, you can clearly see that the neighborhoods with higher percentages of minority groups, such as the area circled in white located in Queens, have higher overall PM2.5 emissions, and neighborhoods with lower percentages of minority groups, such as the area that's squared off in red located in Staten Island, have fewer amount of PM2.5 emissions.
We use correlational analysis, which is a method used to measure the extent to which there's a relationship between two variables. Using this, we are able to see an indirect relationship between PM2.5 distribution and median household income, as well as race and ethnicity percentage. The trend lines in the graph help define this relationship between PM2.5 and income, because although the graph shows fluctuation on both ends of the income ranges, there are typically smaller PM2.5 distributions on the higher end. This is seen in Queens, where the trend line declines from an average of 7.55 to around 7.33 micrograms per cubic meter of air. And for Staten Island, the trend line declines from about 7.08 to 6.92.
With this being said, although the extent to which the relationship between all these variables may not be as drastic as we first hypothesized, it still shows a correlation between them. So in order to mitigate the disparity between different ends of socioeconomic statuses, there should be some policies and initiatives put in place to curb the current trend. Some of the most important ones are the green infrastructure projects and the stricter regulations and assessments of air quality. While conducting this research, some of the hardest challenges we faced were organizing the data to make it usable and creating graphics that help accurately visualize our findings.
For the last 5 weeks, I was able to get more insight on how to use numerical data in visual ways. In addition, I love being able to create connections with peers and mentors in our AQI team. So I'm super grateful to have been able to participate in this opportunity.
This hands-on involvement deepened my understanding of data-driven research methodologies. I'm so glad I had the opportunity to work with such a diverse team in order to make an environmental difference.
Thank you, and a special thanks to our mentors.
Hi everyone, this is our project evaluating the effects of public transit on urban air quality. My name is Igor Borisini and I attend Chaparral Star Academy in Austin, Texas.
I am James Park. I attend Vandergrift High School in Austin, Texas. Let's review some background information. Vehicles emit PM2.5, a particle that can negatively impact air quality. Policymakers need to understand this relationship so that they can make informed decisions about transportation infrastructure to reduce pollution. How do cities' public transportation systems affect air quality? To answer this question, we looked at 5 major US cities and 5 satellite cities. We also analyzed from 2016 to 2020. We used 2 datasets that gave us PM2.5 concentrations and 3 main variables: transportation costs, ridership, and metro population. We used tools like Panoply and Google Colab to determine the correlations between PM2.5 concentrations and the transportation variables ridership and cost.
So now on to the results. First off, for Los Angeles, we can see that LA and Long Beach both have relatively strong inverse correlations between the PM2.5 in ridership and also PM2.5 in operating costs. It's also pretty easy to understand why this is the case. So LA has a historically underdeveloped and underfunded public transit system, and that negatively impacts its air quality. The lack of public transit forces people to drive their own cars, which leads to more overall emissions. So when LA is able to spend more on transit, it experiences a positive effect on air quality. In both Chicago and Joliet, PM2.5 correlates directly to operating costs. However, ridership steadily decreases throughout the entire period. Now, this might suggest that there was a slight overexpansion in public transit, since the ridership metric here is per vehicle, so the fact that it's decreasing shows us that there's more vehicles operating, yet less people are using each one, and this causes more emissions than are necessary. For New York City and Yonkers, PM2.5 pretty much follows the transportation system's operating costs, while ridership per vehicle remains relatively the same. This shows that the transit system is correctly adjusting its spending and capacity according to demand. It seems that New York's transit system is pretty well optimized, and the fluctuations in PM2.5 are simply due to variations in transportation demand over the years. Unlike in the other cities, Denver's satellite city Aurora does not really exhibit the same correlations as the main city. For PM2.5 in ridership, Denver has a weak direct correlation, while Aurora has a strong inverse correlation. This pattern suggests that the increases in ridership are caused by people from Aurora commuting to Denver, which explains why Aurora's air quality improves as demand for transportation in Denver increases. Lastly, for Austin, Texas, the variations in PM2.5, operating costs, and even ridership are quite low. Overall, the correlations are pretty weak, with Austin and Round Rock both following similar patterns. Something interesting to see, however, is that the ridership steadily decreased throughout the period, yet PM2.5 was able to stay the same while operating costs increased. This suggests that Austin and Round Rock residents generally use cleaner forms of transportation, as they used more personal transportation while air quality was not yet negatively impacted. So here we have a visualization of all 5 cities and satellite cities' correlations between air quality, operating costs, and ridership. These are all the same R values already shown, but summarized into a graph.
We concluded that there is a noticeable relationship between city air quality and usage of public transport. We also suggested improvements to infrastructure to reduce pollution, such as adjusting funding for transport based on need and switching to cleaner forms of transport to reduce impact on air quality. In the future, we would investigate additional variables such as types of fuel used for transport and extend the scope of our project to include more cities and a greater time frame.
So for the highlights, the best features of the SEAS program for me were the great mentorship and the resources provided, while the biggest challenge was the limited time frame.
For me, the highlights were meeting new friends, people who share my interests, but it was really challenging catching up with the work because I had an overlap in my schedule, which prevented me from attending most of the meetings.
For the reflection, the SEAS program has really sparked an interest in earth science for me, and I hope to apply this knowledge in my future career.
I've always wanted to pursue programming, but SEAS really gave me an opportunity to explore a unique application of that interest.
So we invite all team members on the air quality teams to please turn on their cameras and unmute their mics. The first question is for team number 1. What were the difficulties you experienced with geospatial data?
So I can take this one. So I did a little more of the working with geospatial data, and initially the data set we wanted to work with was in a netcdf file format, which I hadn't even heard of before. So I was trying to figure out, okay, what is this? How is it structured? And a little bit more about how can we download it? How can I actually visualize what this file is telling me? And I had a little bit of background with geospatial, but only a little bit. I'd only ever worked with shapefiles and raster data, so I wasn't used TIFF files, so I wasn't used to netcdfs. That was one of the issues. I can talk about many more, but yeah.
Okay, for team number 2, do you have any nearby air pollutant resources in your study area, both in Houston and Bayamon?
Yeah, I can take this question for the Houston area. So one of the main pollutants in Houston would be the city. Houston is very urbanized, and especially with nearby oil rigs and things of that sort, there are a good amount of air pollutants from that source.
Okay, so
Go ahead.
sorry. At Bayamon, around 3 kilometers away from the study site, there's the San Pablo power plant, and that usually functions with oil, and that's one of the main air pollutants here.
So one of the questions was, how did you choose Houston and Puerto Rico as your sites? And it sounds like that's where the 2 of you are from. Is that correct?
I'm actually from the Dallas area, but in Dallas, there aren't very great water tracking resources like there are in Houston. So I still stayed kind of local within Texas, but that's how I chose Houston.
Perfect.
Yeah, the same thing happened to me. I'm from Manatee, but we don't have many track on the water quality, so I choose Bayamon that has a few more sites.
Great. Team number 4, did you find anything surprising while you were doing your research?
I think the most surprising thing was the fact that the correlation between the air quality and income and also race wasn't as drastic as we thought it would be. We thought that we would see more differences between the high income and low income communities, but we really didn't.
So our same team number 4, are you aware of any measures taken in your study area to reduce air pollution related disparities? Anyone on team 4?
I think there are basic measures taken in place. Like, even though New York City is pretty industrialized with corporate and both residential areas, there are places designated for smoking, and then also just air pollution's a problem in general. So I think in order to curb that, they're trying to reduce it using measures like that.
Right.
Yes.
Team number 4. Oh, so if you have an addition.
Yeah, I was just saying New York City has started recently started adding a lot of more green infrastructure projects, which has helped out with the air pollution in the area.
Perfect. Team number 5, what other variables would you consider including if you had more time?
So one variable that we wanted to include, but we weren't able to, is the types of vehicles and what fuels they consume. Because, for example, if we could look at trains, buses, or electric buses, then we'd be able to make real suggestions on what to change the transportation systems to.
So that leads perfectly into the last question for team number 5. What policy would you suggest to policymakers?
Yeah, so it really depends on the city, but the strongest suggestion that we have is for Los Angeles to increase spending on public transportation because to this day it's still very underdeveloped.
Great. Well, you all did an excellent job, and thank you for your research. Our next team presentation will be from the Engineer Your World team. Project mentors are Stephanie Hanover. Miss Hanover is a classroom teacher in Bryan, Texas. Sorry, she challenges students to become creative thinkers, problem solvers, and difference makers. So please welcome the Engineer Your World team with their research on exploring Enceladus.
Hello everyone, welcome to our Tiger Exploring Enceladus presentation by the Engineer Your World team for CEAS 2024. Our objective is to design a mission to explore Enceladus, one of Saturn's icy moons. We aim to study Enceladus extensively by analyzing its surface material and subsurface ocean liquid. Tiger will advance remote sensing, orbiting, landing, and thermal drilling technologies, setting a precedent for exploring other icy moons and exoplanets. Our goal is to assess the habitability and potential for prebiotic life on Enceladus. Tiger stands for Thermal Investigations of Geothermal Regions of Enceladus, paying homage to the planet's hydrothermal events and Tiger Stripe landforms. Our team of 8 is split into Team Gaia, responsible for the land distrust system, and Team Poseidon, responsible for the water sampling system. My name is Kinder Wilson, and I live in Minneapolis, Minnesota, and go to school at Phillips Exeter Academy.
Hi, my name is Christian Diaz. I'm from Houston, Texas, and I go to Esper Southeast.
I'm Rohan from Westwood High School in Austin, Texas.
Hi, my name is Nehemiah Chow. I'm from Austin, Texas, and I'm homeschooled.
Hi, my name is Lisa Hodoroshkova, and I live in Tumble, Texas, and I attend Tumble Star Academy.
My name is Pauline Kaur, and I'm from Yuba City, California. I am from Red Valley High School.
I am Colin Lukes, and I am from Powers Lake High School, North Dakota.
Hi, my name is Mihir Ganavarpu. I'm from Katy, Texas, and I go to Jordan High School.
This is our mission patch. The centerpiece of the mission is Enceladus, and its parent planet, Saturn, is displayed in the background. The 4 tiger stripes that we plan to study are overlaid on top of the moon. Inside one of the tiger stripes is a cross-section of Enceladus to display the icy crust and subsurface ocean that we plan to study in our mission. The mission name, Tiger, or Thermal Investigations of Geothermal Regions of Enceladus, is boldly displayed across the center of the patch. The border colors also reflect the same theme as the cross-section, where there's an icy blue exterior and a dark blue interior. Each of the last names of our team members are displayed on the exterior layer of the patch.
Enceladus has emerged as a compelling destination due to a confluence of factors. It has a subsurface ocean beneath its irregularly thin ice crust on its south pole. In the ocean, there's a high possibility to study potential extraterrestrial life. During a flyby through the ejected plumes from geysers, the Cassini spacecraft collected samples of the dust and ice from the plumes and detected the presence of CHOMPS elements. The presence of these elements have elevated this moon to the forefront of astrobiological research. CHOMPS elements are fundamental building blocks of life, and their presence significantly enhances the possibility of biochemical processes occurring. In the South Pole, there's an active area called the Tiger Stripes. These Tiger Stripes consist of 4 subparallel linear depressions that allow the subsurface ocean to exit, making geysers. These geysers constantly shoot water at high speeds out of the exosphere where it freezes and falls back down to the surface. The exact cause of the formation of this feature is still unknown, but many speculate that there are hydrothermal vents on the ocean floor that cause these activities to exist. All these features make Enceladus a prime location for research and space studies.
Prior to planning specifics of our mission, we outlined our mission's 3 main goals and their scientific importance. The first goal was to understand the structure and material composition of Enceladus's icy crust and subsurface ocean. This will help us locate any potential regions of interest based on surface or geothermal features, plan future landing sites based on the ice depth and geyser locations, and gauge the stability of any potential habitable zones in the ocean. We also want to search for indicators of habitability, life forms, and unique chemical composites. This would provide us with an understanding of the potential habitability of Enceladus. Moreover, it is crucial for us to detect CHOMPS, the fundamental building blocks of life, as well as any potential organic or inorganic compounds that might suggest the presence of prehistoric microbial life. Lastly, we aim to collect information for future missions into icy moons. This will be done through analyzing the results of how our drilling system and sampling system move through the crust and subsurface ocean of Enceladus. Moreover, we will be able to learn about placing an orbiter in Saturn's rings, which could help for an exploration to other Saturnian moons such as Titan.
For our brainstorming process, each of our team members came up with unique ideas to accomplish the 3 goals of the mission. Each member researched Enceladus through NASA treks and previous mission designs to generate ideas of components that would be logical and optimal for our mission.
3 ideas were created by each team member, and each idea was critiqued by the 3 members of the sub-team. Some ideas included orbiter satellites as well as AUVs. Then each member used a constructive criticism received from others to create a final idea sketched individually. Sub-teams combined the individual ideas to come up with a theoretically sound and plausible final design, which was used as a basis during the building process. Within the sub-team discussions, we were able to overcome multiple pseudo-restraints that individual ideas had by taking the best aspects of multiple designs into account. Ultimately, our 2 sub-teams, Team Poseidon and Team Gaia, created a visual display of the final design while continuing to research materials, geological aspects of the mission, and to improve the design over time.
During the prototype phase, Team Poseidon honed in on the challenge of reaching the subsurface ocean and collecting water samples. We engineered a sophisticated thermal drill design inspired by previous cryobot designs such as Archimedes or Recos. After making this design, we decided to create a prototype of the water sampling system that would fit the constraints of our drill.
Team Gaia decided to focus on the task of landing on the surface of Enceladus. During the preliminary stages, the instruments required for accomplishing the goals of sampling falling ice, as well as the packaging and deployment mechanism of the drill, were used to design a detailed lander. Through discussion, we reached the conclusion to prototype the thruster system of the lander and test the use of angled thruster mounts for minimizing horizontal velocity when landing on a low-grip surface such as the ice on Enceladus. The goal of the prototype was to simulate a real landing scenario by mimicking thrust in Enceladus's low-gravity environment, which is 1/100th of Earth. We intended for the propulsive lander to help us simulate the lack of an atmosphere on Enceladus and further our knowledge of the mechanisms required to land on the surface of Enceladus.
Next, our subteams we began building and constructing our prototype. A wide plethora of tools and methods were used to build the various ideas we had designed. To build the physical prototypes, each subteam went through an intricate and tedious build process. Nevertheless, each member's collaborative efforts and technical skills were used throughout the 2 weeks to build all of the mechanisms needed for testing our designs. Both subteams had to make a multitude of edits to the prototype through the building process to ensure that it was best suited for our mission.
The team began the building process by creating drawings of our water sampler. We each researched various designs of water samplers to see which mechanism was best suited for how we were collecting samples. From there, we came together as a group, created the design we thought best, and sketched it out. This drawing was then translated onto a 3D computer-aided design file. Based on the design, we compiled a parts list for our sampler, and once we had our materials, the build began. We started with making the housing for the sampler, then we added the pipes to hold the water. Next, we added tubing to the pipes and a water pump with its electronics. While we coated the electronics, we added a watertight seal around any materials that touched water. Once all the components were coated, we created a 2.5-minute activation timer, during which we had to put circuitry into the pump and get it into the testing environment.
Our testing process, in contrast to our building process, was a much shorter ordeal, which consisted of only 3 trials of an automated water pumping period. Upon the completion of the previously mentioned 2.5-minute activation timer, a 12-volt diaphragm water pump, operated by an H-bridge motor driver, filled about 3 storage valves with water during a 25-second pumping period. All the while, a simulated gaseous sample analysis was performed by telemetry that recorded temperature and humidity, DHT11. Side movements were recorded by an accelerometer and gyrometer, the GY521, which respectively reported acceleration, rotation, and more temperature data. An OB7670 camera, GSN SR4T, and HC06 Bluetooth module were additionally planned to process visual data, emit sonar signals underwater, and allow remote terminal operation. However, time limitations prevented their addition, and the components were not necessary.
Next, Team Gaia began by identifying the parts required for the lander as well as the timeline of construction. We began by identifying the sensors and electronics required to move and control the lander, using the ultrasonic sensor to sense the distance between the ground and the lander, as well as the gyroscope for orientation control. This would allow us to control thrust based on the altitude at an individual motor level. We decided to use an Arduino Mega as well as the IDE software to regulate thrust and manage orientation as well as altitude. We soldered each of the 4 motors to their respective speed controllers and wired the controllers in series to our Arduino. We made use of a separate breadboard to expand our ground wires for using the gyro and ultrasonic sensor. Next, we made use of wooden dowels and 3D printed components when connecting the 4 load-bearing legs, which would house the legs for the lander as well, to spread the force of deceleration across the lander and be able to support the instrument suite as well as the drill deployment mechanism that would be on top. We tested our lander in 3 separate stages, including power delivery, thrust, and automated distance measurement. This allowed us to test each aspect of the drop in a controlled manner without having to actually test the drop, which might present some other variables.
Designating materials for future missions is complex, so we chose to use proven materials from previous missions. Although these may be replaced by future innovations, we use current concepts sparingly. Our design priorities were materials resistant to extreme cold, negative 200 degrees Celsius, and radiation. Suitable materials already in use on spacecraft include aluminum alloys for their strength and lightness, titanium alloys for durability and performance in code, reinforced carbon polymers for lightweight structure, and multi-layer insulation for radiation protection. Alternative materials like aerogel show promise, their full utilization has yet to be realized, and with the travel towards Enceladus taking years, questionable materials aren't ideal.
At this point of the mission, the subteams reconvened into one group and began combining the 2 separate ideas. We made the overall plan of the mission from the orbit to the drilling.
Our mission consists of 3 main components: the orbiter, lander, and drill. Our orbiter will stay in orbit for 2 years, and during these 2 years, the orbiter will collect an assortment of valuable data. Among the data will be a detailed map of the surface of Enceladus. This is vital to the second component of the mission, the lander. With this detailed map, we will finalize our landing location in the South Pole near an active geyser and send down our lander. The lander will hold all our instruments, which will be used to get data and analyze data from our surroundings and samples. Additionally, our lander will also be housing the third component of the mission, the drill. This drill will dig through 5 kilometers of ice to reach the subsurface ocean, where it will gather samples and then proceed to bring them back up to the lander for analyzing.
The orbiter would perform multiple flybys, getting gravitational assist for getting to Enceladus. As Saturn's natural satellite is located within Saturnian rings, the orbiter would take on a period 3 halo-shaped orbit, as a safety precaution and ability to conduct more detailed observations. The satellite would go around the moon with an average velocity of 250 meters per second. The orbit would be focused on the first liberation point, as it would provide more stability and safe fuel. Also, choosing to go around at this equilibrium point would provide us with a closer look of the South Pole. More specifically, the ground tracks of the orbiter would go straight through the tiger stripes. Now that we have talked about the orbit, let's transition into our actual orbiter's design. It is heavily influenced by 2 Earth satellites, ISAT-2 and GRACE. The spacecraft will be powered by gallium arsenide solar panels that ensure that it is light, sturdy, and sufficiently powered. The orbiter would receive the signals from the lander and send them to Earth either directly or by bouncing them off of Mars Renaissance orbiter in case of an obstacle blocking the path. The orbiter would carry their radar for icy moon exploration to track the thickness of ice, a thermal infrared scanner that will create a temperature distribution map, a high-resolution camera high-rise to take pictures of the surface, and a gravimeter would measure the fluctuating gravitational pull. Through the collected data, the orbiter would be able to choose the exact location where the lander will reach the surface.
The landing location needed to be a place that did not have rapid changes in elevations that could cause damage to the lander upon landing. Furthermore, we decided not to land directly on a tiger stripe or geyser, but rather land close to them to be able to fulfill our goals without being directly on top of the high-speed geyser debris. Since the thermal drill will be deployed directly from the lander, and our dust collector will also be from the lander, our optimal location must still be in close proximity to a geyser. Finally, we wanted the point to have a low surface elevation so that the drilling distance is minimized. Based on these points, we decided that the lander will land within 5 kilometers of the region bounded by the coordinates, with a latitude of approximately -83 and a longitude of about 321 on the Baghdad stripe, which is the second stripe from the left shown here. This location has an elevation of -450 meters relative to surface level and a geyser within 6.4 kilometers of the center of the landing zone labeled on the dotted line in the image.
The lander will house our drill, sampling devices, sample analyzers, and will be powered by an RTG. It will be made with metals, composites, and insulation materials, all of which will be extremely tolerant to radiation and cold temperatures. Enceladus has no atmosphere, so thrusters will be used to guide our lander and slow down our descent to our selected location. Once on the surface, the lander will have a system to anchor itself into the ice and start recording data about its surroundings using a Mastcam-Z. The camera will allow us to send high-quality panoramic photos back to Earth. We will then proceed to take the samples of our surroundings with our ice and dust collector. The collector will be shaped like a funnel and will be able to catch the ice being expelled from the geysers and the interstellar dust that falls with the ice from space. The dust will be sent through a dust analyzer in the lander, and the ice will be sent through our sample analyzer process for analyzing. Our sample analyzer process will be using an assortment of instruments to give us a detailed idea of what elements, molecules, and chomps exist on Enceladus. All the data gained will be sent back to Earth, and we will be able to have a detailed idea on what exists on Enceladus.
Our final drill design utilized a myriad of different components to ensure that we are able to effectively get in and out of the icy crust with our collected water samples. Starting from the bottom, we have our lower drill. This drill utilizes the direct laser penetration technology aboard the Archimedes drill to create a highly concentrated thermal beam and melt through the ice, as well as mechanical drilling to form an initial divot. Above is a temperature sensor, followed by the next major component, which is the water sampling system we discussed previously. Moving up from the water sampler is a large wiring section, followed by a sensor complex. We then have a movement system that controls precise transitions in the XY plane and the small plutonium oxide RTG for powering our drill. Finally, after the tension and load sensors, we reach the upper melting tip. This is a heat-based drill that will be used for sample recovery by drilling upwards and heating the tether it is attached to so it is able to move. To understand the functionality and feasibility of our design, we created the table on the left to analyze metrics such as energies, masses, analysis targets, and outputs of the instruments aboard the orbiter, lander, and drill. We can see that the scientific payload is relatively inexpensive to power and move. The shortened Science Traceability Matrix, or STM, on the right is used to show how each instrument answers a specific part of the mission objectives and to show that every instrument contributes to completing our mission. The elements are as follows: radar for icy moons, RIME, high-resolution mass spectrometer, HRMS, thermal infrared scanner, TIRS, GRACE gravimeter, high-resolution imaging science experiment, HiRISE, MASSCAM-Z, quadruple mass spectrometer, QMS, gas chromatography mass spectrometer, GCMS, microscope, nanopore, electrochemical sensor array, ESA, and finally an alpha particle X-ray spectrometer, or APXS.
During the mission, we encountered multiple challenges, but we were able to identify methods that could successfully investigate icy moons. At the same time, we designed our mission in ways that could be the foundation for future exploration, understanding, and observation of Enceladus.
Some challenges we foresee in the future are communication with Earth due to the distance between Enceladus and Earth, radiation damaging to our instruments, and the extremely frigid temperatures of Enceladus's icy crust and subsurface ocean. Landing on the icy surface of Enceladus also brings the challenge of no atmosphere. Our greatest challenges were regarding power and minimizing the uses of RTGs alongside engineering a method to collect water samples that is reliable and recoverable.
For future missions, developing an alternative method to power the satellite that does not rely on solar energy is crucial. As the south pole of Enceladus enters the fall season, the area would be submerging into darkness. Further advancements of the sustainable power systems that can be utilized beyond the Jovian system would provide us with a longer living mission that would be able to still be active during the dark periods. Also, continued technological developments should take place to design a mechanism to go further down in the ocean. Exploring the depth of the ocean would provide us a more detailed composition of the water, as liquid closer to the surface loses some of its chemistry. Lastly, we believe that in the future missions, mapping the core of Enceladus should be prioritized, because the irregularly shaped core could hold the answers to the activity happening on the South Pole.
The proposed mission to Enceladus, Tiger, offers significant scientific benefits by advancing our understanding of Saturn's intriguing moon. By studying its surface material and subsurface ocean, Tiger aims to assess Enceladus's habitability and potential for prebiotic life. Data from the lander's sampling devices, thermal drill, and orbiter remote sensing will provide comprehensive insights to the composition and formation of Enceladus's subsurface oceans. These findings could also inform our understanding of other icy moons, broadening knowledge of potentially habitable environments in the outer solar system. This mission will advance remote sensing, orbiting, landing, and thermal drilling technologies, setting a precedent for future exploration. Overall, Tiger ensures a thorough investigation of Enceladus's potential to support life, contributing valuable data for future missions and enhancing our understanding of astrobiology and planetary science.
During the short 2-week period at SEAS, I have learned many wonderful things. SEAS has been pivotal in my ability to work with a team to teach and be taught different skills like coding, soldering, CAD, and the engineering process. I can confidently say that SEAS has been a life-changing experience for me.
Although not proficient by any means or stretch of the definition, I can confidently state SEAS program's greatest effects on me was increased knowledge and perspective for other specialties of STEM such as coding and wiring. The presence of various teammates have undoubtedly served as beacons of new perspectives, which have already reignited my passion and secured my passion for STEM as a whole.
In only 2 weeks, the SEAS program has been instrumental to augmenting my technical and collaborative skills. Working within a team, conducting intensive research, and building a mission from scratch with Arduino's CAD and PCB gave my programming skills a platform to be authentically and impactfully leveraged. My teammates have only further stunned me with their ingenuity and skillful implementation of their talents, and our mentor has been a spark of joy in our everyday lives.
I am very grateful for my time with the SEAS program because I got to meet so many people with the same interest as me, as well as conduct genuine research, which only elevated my interest in entering the STEM field.
I have had a wonderful time at SEAS. Being able to work with mentors who are actively in the industry and hearing from astronauts has truly inspired me to continue to pursue a career in aerospace. Additionally, working with other interns and researching about our mission has sharpened my STEM skills and has also taught me new skills. I will forever be grateful for this opportunity, and I hope to continue to work with y'all in the near future. Thank you.
SEAS has been truly a life-changing program. I'm confident to say that SEAS has changed my view for my future for the better. I am so beyond grateful for this amazing opportunity and have learned so much about NASA and working on missions. Thank you so much.
The SEAS program has taught me a lot about collaboration on an engineering project. Going through the entire design process as a team and picking up skills along the way has made SEAS an incredibly beneficial experience that will go on to aid me in my future endeavors.
The SEAS program has been a transformative experience, enhancing my technical skills and teamwork through hands-on projects involving coding, CAD, and mission design. Learning from industry mentors and collaborating with peers who are passionate and proficient in a variety of fields has inspired me to pursue a career in aerospace and STEM, leaving me grateful and more prepared for my future endeavors.
We've been fortunate to meet multiple experts to consult for our mission. Dr. Leonard, a member of Planetary Geosciences at the NASA Jet Propulsion Laboratory, JPL, advised us on the geological factors of Enceladus. She advised us with important information on selecting the landing site. Professor Adam Noakes is a lecturer at UT Austin. With his realistic approach to our mission, he guided us to act within reason and proposed a few resources for us to use. Lastly, but certainly not least, we also consulted with Brian Day over a Zoom meeting concerning NASA treks and planetary imaging. Day works with NASA in the planetary sciences.
Thank you! So I want to invite all members of the Engineer Your World team to turn on their cameras and unmute their mics. We have several questions. The first is, what would you expect to learn by sampling the water on Enceladus?
I can take that. What we would learn by sampling the water in the subsurface ocean of Enceladus is, firstly, we would be able to detect CHOMPs, which is carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are like the key building blocks of life. Moreover, we would also be able to detect potential microbial life forms, so like small bacteria in the water. We'd also be able to sample the water in the subsurface ocean of Enceladus and compare that with our water on Earth and potentially water in other icy moons like Europa to see how life might form on Enceladus compared to how it is formed on Earth.
And the next question is, what is RTG?
Yeah, I can take this one. So an RTG is a radioisotope thermoelectric generator. It's just a really long name, but basically it generates electricity by relying on the Seebeck effect, which is basically transforming heat from isotopes such as plutonium-238. And it basically relies on converting heat from radioactive decay into electricity. And it's one of the most reliable forms of electricity that's been used on some satellites, such as the Cassini mission that also did a flyby of Enceladus. And what we're working with here is kind of scaling up the power due to the more power-intensive systems of our mission.
What would you consider were the biggest challenges in your design?
I got that. So with in our sub teams, our group had the water sampler, and when we went to go look up like some 3D designs or research papers about the actual sampler, we couldn't really find much research on water sampling mechanisms outside of ones that have been used in the Antarctics and stuff like that. So we had a little bit of trouble trying to design our own water sampler for Enceladus from there. And during the building phase, we miscalculated the thickness of our materials, and we actually swapped the amount of tubes to collect the water from 4 to 3 because we had a limited amount of space.
Perfect. And if you were able to have follow-up sessions with your team to continue this project, what would you focus on in future investigations?
I can take this one. I think if we had like more follow-up sessions, we would be working on going deeper into the subsurface ocean, because the deeper we go in, the more chemistry there is on the bottom of the ocean, and we can get more exact results from it.
Perfect. Well, you've done an excellent job with your research. I applaud your outstanding results. Our next team is the Exoplanet team, led by project mentor Thomas Rutherford. He is an adjunct astronomy professor at East Tennessee State University and has led high school students conducting astronomy research since 2006. Please welcome the Exoplanet Transits team with their research on detecting planets around other stars.
Welcome to Exoplanet Transits. Our group was led by or mentored by Dr. Thomas P. Rutherford, and our group is composed of
Soham Gautam,
Samanya Girish,
Ethan Liu,
Amay Nani,
Andrew Rubello,
Hridaya Saravanan,
Luke Toman.
First, let's dive into what exoplanets are. They're planets that orbit stars other than our sun. Now, there are many methods, but we're going to talk about the 5 most important. The first is radial velocity. Now, this is using the Doppler shift to derive information about its period and velocity. Next, we have the transit method. Now, this is the method we'll be using, and we watch for dips in the absolute magnitude light curve. Next, we have the direct imaging, which is essentially taking pictures. We then have gravitational lensing, where we use we use the ability of light to curve around large masses as a gravity lens in order to detect exoplanets far away. And finally, astrometry, which is basically watching for wobbles in the host star of that exoplanet. Let's move on to the exoplanet history. In January 1992, the first exoplanets were discovered by Wollaston and Frail. In 1999, we observed the first transit independently led by Charbonneau and Henry. And lastly, in April 2001, the first exoplanet was discovered in the habitable zone. Now, this is the zone where it's not too hot or too cold for life, and conditions are, at least for life as we know it as humans, and it was in that zone that was just right to facilitate life. Next slide.
These are some of the primary reasons why astronomers conduct research on exoplanets. By researching exoplanets, we can find Earth-like planets in other star systems, and if they are in the Goldilocks zone, as in within the appropriate range of distance from a target star, they could potentially support life. Also, studying exoplanets can give us insights into the planetary processes that occurred in our own solar system during its formation, including that of the Earth. Finally, as the search for exoplanets continues and we find new ones that are potentially habitable, we also continue to attempt to answer the question of, are we truly alone in the universe? Next slide. The most common way of detecting exoplanets is through the transit method. To detect a transit, the observing instrument, such as a satellite or in our case, a ground telescope, must be recording the magnitude or brightness of its target star over an interval of time. In the animation shown, we can see how graphing the brightness versus time data can produce a light curve, which can tell us more about the transiting exoplanet and its host star. Next slide. When graphing the magnitude of the star over a given time interval, if an exoplanet is transiting the star during that time, a dip should be visible in the light curve graphed. The depth of the graph transit depends on the size of the exoplanet and the size and brightness of the star. In the two cases shown on this slide, we can see exoplanets of the same size transiting a brighter star on the left and a dimmer star on the right. The transit on the left will produce a shallower light curve because since the star is relatively brighter and more massive, the exoplanet will block a lesser percentage of the star's light as it transits. On the other hand, the transit on the right will produce a much deeper light curve because even though the exoplanet is the same size as the one on the left, it will block a larger percentage of the dimmer, smaller star's light. Just as there are different types of planets in our own solar system, exoplanets come in varieties too. While there are many subcategories that exoplanets can be further classified into, there are generally three main types: Jupiter-like, Neptune-like, and Earth-like. However, of the exoplanets we have discovered, hot Jupiters have been the most common to find, with other types being rarer to discover due to the difficult nature of finding them. Hot Jupiters are large gas giants having a size similar to Jupiter and extremely hot temperatures since they orbit really close to their host star. This is the type of exoplanet that is most easy to find because they produce the clearest transit as a result of their large size and close proximity to their star. Next slide. While transit methods are the most common way of finding exoplanets, this method does have its own limitations. For one, it is really hard to find smaller exoplanets that orbit larger host stars because the graphs their transits produce have dips that are too shallow to notice. Also, it is easy to detect false positives or graph transits that look like they were made by transiting exoplanets but were actually caused by something else, like brown dwarfs that look similar to exoplanets or stars orbiting each other in a binary star system. Next slide.
So in researching these exoplanets, there are two goals of our procedure. One of the objectives is to use the data to examine the changes in brightness of the stars, since the dips in the magnitude demonstrate an exoplanet in transit. We measure the brightness with its flux, which is the amount of energy from the star that reaches whatever is detecting it. The other aim is to determine the mid-transit times of the exoplanets, which is when the exoplanet is directly in front of the star. These times are calculated in Julian days, which are the amount of days since January 1st, 4173 BC. Next slide. In this project, the procedure started with collecting the data. The images for the data were taken over a period of a couple hours using the CCD cameras on SARA telescopes. SARA is an association of colleges and universities that operate 3 telescopes around the world, those being SARA KP, SARA CT, and SARA RN. East Tennessee University is part of that consortium, which is why we were able to access these images. Next, these images must be calibrated since there are external forces that affect the image. Calibrating the images uses 3 types of frames: flat frames, dark frames, and bias frames. About a dozen flat frames are taken and then averaged in order to account for the noise and dust in the image. These are taken by pointing the telescope at the sky at a uniform surface. Dark frames are used to eliminate hot pixels, which are when some of the pixels of the CCD camera generate an electron as if they were struck by photons when they really weren't, creating star-like particles in the image. Dark frames are taken with the camera shutter closed to detect the hot pixels so they can thus be subtracted. Bias frames are 0-second exposures to cut out the tiny electron current the CCD can detect from electrons that are just generated from the camera being on. Next slide.
AstroImage-J is the primary program used by astronomers for general photometry. There were 2 different ways in which we looked at these transits using AstroImage-J. The first is individually selecting the target and reference stars for each data file, and then once the reference star's magnitudes are inputted based on data from the star chart, the target star's magnitude is then calculated by the program. This process is repeated, and we plotted all of the results on an Excel graph. The second way we examined the transits was compiling all the images at once for AstroImage-J to analyze. The same process of identifying target and reference stars are used, and the program can then identify the corresponding stars for all of the images. A graph of the target star's magnitude is then produced, where we can visualize the transit. However, even when doing all images at once, AstroImage-J was an unideal software to use. Instead, we primarily used another software that has better user interface and is more advanced in order to create a best fit line, and that was Holloman Photometry Software, or HOPS. Next slide.
All right, I'll be walking you through the process of making a graph that shows this dip in the light curve with the HOPS software, as Ethan mentioned. So the first step is to import all of your images into the HOP software, and these images are in the form of FITS files. This stands for Flexible Image Transport System. And so after clicking select change directory, you point it to the directory with all of your images. And then in this observation files, you type in the first letter of what the star is, and then it should show how many files or images you have of the sky. And in this case, we have 85 files. The next step is to click on the Show Header button, which essentially displays the metadata about the images. It shows who took the images, with what filter did you take the images, from where did you take the images. And after looking at this header data, you can fill in the filter, the camera filter. Then the next step is to select the target star. What star are you actually looking for? And so in this case, it was WASP 43. WASP stands for Wide Angle Search for Planets. And you should just type it in, it'll identify star if it's in the HOPS database. The last step is to identify the location of the telescope. And this specific, this imagery was taken from the CTIO telescope in the Sierra Consortium. And so these are the latitude and longitude coordinates for that. And so after that, you just say save options and proceed, and you move on to this step, which is identifying the target star in the image and then the reference stars. So this can be a tedious process because sometimes you have to identify the star you're looking for in an image like this. And so this is a hard process, but then there's this option which says plate solve image, which essentially identifies the star in the image for you. And the target star is this red, is what this red arrow is pointing to. And these blue dots are the reference stars. And their purpose is to essentially make sure that there's no abnormalities in the sky that's changing something in the brightness of all these planets. So they're just a reference. All right, now when you run the photometry, it should go through sequentially all 85 images in this case, and it should identify dips in the brightness that each star is emitting. And as you can see with the target star, as it goes through these 85 images, it identifies that there is less brightness at some points, and this is the dip we're looking for. Whereas in the reference stars, it's sometimes noisy, like this comparison star, but it's supposed to be like this, where nothing's happening to the star. And so after you generate the graph, this is what it'll look like. On the x-axis, you have time, and essentially you're looking for this dip in the light curve. So on the y-curve, you have the relative flux, which is an astronomer's term for the energy which is emitted by a star, or the brightness. And so you can see on this graph, bottom left, that there is this dip in the light curve for the specific star. And the x-axis, as I said, it's time in Julian days. The amount of time which the exoplanet is transiting the host star for can give you an idea of how large this exoplanet is. It could give you data on the radial velocity of the planet. Another thing is that if this dip is larger, that means more light is being blocked by the exoplanet, meaning that it's either larger or the host star is smaller. So you can extrapolate data like this. Moving on to results.
So for our results, we were able to detect transits for multiple exoplanets. On the left is a graph for WASP 98b, which was discovered in 2014. Some general information about this exoplanet is it's a gas giant with a 3-day orbital period and a planet mass of 0.922 Jupiters. And according to the best fit model generated by HOPS, the predicted mid-transit time occurred on 2,460,282.59349 Julian days. And the observed mid-transit time occurred 3.3 minutes before what the model had predicted. Next slide. Another transit we detected was for Kepler 41b, which was discovered in 2011. It is also a gas giant, and it has an orbital period of 1.9 days and a planet mass of 0.56 Jupiters. According to the Hopps-Bespet model, the predicted mid-transit time occurred on 2,460,156.46348 Julian days, and the observed mid-transit time occurred 1.2 minutes after what the model had predicted. Next slide.
All right, so moving on to our third exoplanet, WASP 135b, as you can see by the graph, the dip is very shallow, even though this gas giant has a planet mass of 1.9 Jupiters, which is a little bit strange, but nonetheless, it is a gas giant. It was discovered in 2015, and its mid-transit time is 2,460,155.43458 Julian days. And it was observed 7.2 minutes later than expected. And it does orbit a relatively cool G-type star, which is very faint to be seen by the naked eye. Next slide, please. And looking at TRES 5b, the dip is much deeper, and it is also a gas giant as the other three were. It was discovered in 2011, and its planet mass is 1.79 Jupiters. And it does orbit a K-type star, which is also another relatively cool star, too faint to be seen by the naked eye. Its mid-transit time was 2,460,183.47864 Julian days, and it was observed a little bit before than expected. Next slide. So in looking at the overview of all of our exoplanets, we can see that we have a small sample size of only 7 exoplanets, so we can't really conclude much. However, there are some things to note from this data. For one, WASP 96b has the earliest mid-transit time, so we can see it dip in brightness first. And in looking at the exoplanet size, these exoplanets are similar to or greater than the size of Jupiter, as you can see the size of exoplanet column. And then lastly, WASP 135b is the biggest relative to its star, 16.8% of its star. However, it does have one of the shallowest dips, so that is a bit interesting to note. And another thing is that this star also has the biggest disparity between the time it was expected to transit and the time it actually transited. Next slide.
While most of the exoplanet transits we looked at have a confirmed exoplanet orbiting the star, that is not the case for TOI 2823b, or Test Object of Interest 2823b. While the photometry analysis we performed created a relatively significant dip in the star's brightness, the dip was sporadic and not exactly clear. Hence, the Hopps program could not produce a line of best fit for the transit, but these are promising results for a possible new discovery. We were still able to calculate a prospective mid-transit time due to the dip, but not much else could be concluded. Next slide.
Some of the highlights of our project was we were exposed to observational astronomy techniques that were practiced by scientists worldwide.
We were able to perform real-life data analysis using specialized software.
We were given the opportunity to contribute to and submit data to the NASA Exoplanet Archive.
We were able to engage with the CEAS e-learning curriculum, which guided us through the fields of Earth and space science. And we also got to learn about Python data visualization through these softwares that we used. Okay, some personal reflections of the CEAS program. I personally loved the opportunity to engage with astronomy data, image data at one of the largest space and Earth research centers in the world. So it was a great opportunity to meet my fellow peers, be mentored by our mentor. Yeah.
The CEAS program gave me the amazing opportunity to work with astronomical data sets and applications. I'm so grateful I could work with this team and with the Exoplanet Transits project because it guided me towards a career in engineering and astronomy.
The NASA SEAS internship program gave me the opportunity to work with other high schoolers in a scientific setting to pursue my passions as a student. SEAS was able to provide me with a project adequate for high school students where I could harness my background knowledge in astronomy and astrophotography and still be able to perform meaningful research with the team. This experience both propelled and replicated what I hope will be a future career in astronomy.
This internship was an amazing experience for me. I learned a lot through the e-curriculum and also through our mentor and my peers. And this project has taught me a lot and improved a lot of my skills from presentational to software to data visualization. So I learned a lot, and it allowed me to pursue my passion in astronomy by engaging me in really hands-on experience. And it also gave me the opportunity to benefit the scientific community by researching exoplanets, which is a common research topic and a very important research topic. And it also allowed me to use the Python software to graph and visualize data that we received from outside sources, which is a new experience. So I'm forever grateful for this opportunity in NASA season.
For me, SEAS really gave me the opportunity to learn from an experienced astronomer. And like as a high schooler really passionate about physics, it's really a once in a lifetime opportunity. So I'm really grateful to SEAS and Dr. Rutherford for the opportunity.
And while the process of working with real data seemed intimidating to me at first, the work I did with my mentor and my peers really made it seem less daunting, and it let me head start my career in space science.
Yeah, this SEAS experience has taught me so much thanks to my wonderful mentor and peers. I had no idea about exoplanets or transits before this program, but this program really unlocked a new fascination and it intensified my passion for astronomy.
These are some of the people and organizations we'd like to acknowledge. Firstly, our mentor, Thomas Rutherford. He really guided us through this entire process. And obviously NASA SEAS for allowing us to work on this project, and University of Texas at Austin for giving us the resources to embark on this project. East Tennessee State University is the university that our mentor works for, and they also provided the Zoom meetings and also the data for us to work with, which is also thanks to the SARA Consortium, which is a group of telescopes that we got data from. And AstroImageJ and HOP software, as previously mentioned, it really helped us analyze the data and really facilitated the whole process. And of course, our parents.
These are our references. Thank you very much for taking the time to listen to our presentation.
So we invite all members of the Exoplanet Transit team to open their cameras and unmute their mics. We have several questions for your team. Which method did you prefer for detecting exoplanets?
Well, the focus of our project was really just the transit method, and also the transit method is what's used by most astronomers as the method for exoplanet detection. And as previously mentioned, there are other methods of exoplanet detection like astrometry and radial velocity, but the main focus of our project was the transit method.
How did you choose which images to input into HOPS, or were they provided to you?
We were provided with like a set of images for each exoplanet and star that we did, but within that set, we were able to exclude some based on the quality. So like if they had a dust donut where there's like a black dot in the middle of a star, then we'd exclude that one.
What challenges did your team encounter, and what were ways that you used to resolve them?
Obviously, in certain cases, we would like the data would be kind of unprocessable, or we would have trouble with the data. But I think through communication with our fellow team members and Dr. Rutherford, we were able to overcome those regardless of what came up.
And another question, HOPS seems like a very complicated program. Did you have prior experience? And if not, what was the learning curve for this program? Would beginners be able to use it?
Yeah, so Hops is actually a really easy to use program, and it had a really good user interface compared to what we were using before. And initially it was a bit difficult to get used to because there were many steps involved in it, but our mentor, Dr. Rutherford, really took us through step by step, and if we had any questions, really walked us through the process. So it's definitely beginner friendly as well.
What were challenges that were unique to working remotely with the team, and how did you overcome that?
I know that
Go ahead, yeah.
like working with different file types and having to import all the data into one shared Google Drive could be difficult sometimes, because at times there are like folders that wouldn't open or zip files that couldn't be expanded.
Yeah, just to add on to that, you have to make sure that everyone's software is working correctly as well. If someone doesn't have the HOP software loaded correctly, or they can't import their data set correctly, you have to get them up to speed and caught up so everyone can be on the same page as we move through the project.
Excellent. Well, very interesting project. We will be taking a short break. We invite you to watch highlights from student intern research during the Earth and Space Science and Python coding courses. We will reconvene in 20 minutes at 3:10 p.m. Central Time. So welcome back to session 3 for the NASA STEM Symposium. Our next team presentation will be from the Orbital Debris team, led by Apurva Kara, who is pursuing a doctorate degree in orbital mechanics, area of aerospace engineering, under the supervision of Professor Mariba Jha at the University of Texas at Austin. Her research work involves developing tools for automating prejudice-free decisions in problems related to space domain awareness. Please welcome the Orbital Debris team with their research on geostationary orbit satellites compliance modeling with International Telecommunication Union regulations.
Welcome to Orbital Debris Oversight, fostering space domain awareness through ITU compliance. I'm Nicholas Barr, and the SEA's internship has helped guide my decision to pursue a career in astronautical engineering in the United States Space Force.
I'm Taha Khan, and the SEA's opportunity has been a great experience for me to continue honing my skills in computer science.
I'm Isai, and SEAS has opened up my mind to the possibilities of my career.
I'm Noel Kim, and SEAS solidified my interest in engineering by giving me real-world experiences in the field.
I'm Diana, and SEAS has helped me learn more about our satellites and helped me pursue my passion for engineering.
I'm Riley, and SEAS has given me a more direct experience with researching astrophysics.
It is estimated that there are around 100 trillion pieces of debris in Earth orbit. This can pose a threat to launches and existing satellites due to high velocities. However, what we are concerned about in this project is geostationary orbit, or GEO. GEO sits exactly 35,786 kilometers above the ground. It is mainly used for telecommunications and GPS. While there is little orbital debris in GEO, the number is quickly expanding and needs to be kept clear so geosatellites stay safe. Geostationary orbits offer numerous benefits to humanity because of their unique positioning. Their stationary nature allows them to provide continuous support to ground-based objects, making them indispensable for various applications. However, their crucial role also means that maintaining their functionality is vital. Even a small amount of orbital debris can damage or destroy these satellites, potentially disrupting the essential services they provide. The solution to this is physical slots in the ITU. Physical slots are defined by a longitude to the equator, typically separated by some degrees to avoid interference. This is established by the ITU, which is a branch of the UN that specializes in communication technology. ITU compliance ensures the safety of satellites as long as it is followed correctly.
So with this background, the question that we decided we wanted to focus on was, what is the distribution of geosatellite compliance by country? And the reason we wanted to focus on this is because we decided that if we were to implement a solution in the future to encourage compliance internationally, we would need to know which countries are the most responsible for the population of non-compliant satellites, and that would help us, determine how a solution should be administered across different countries. So that led into our project goals, which was first to analyze the current geoposition compliance situation, and second, to come up with some solutions or starting points for improvement in these regulations. And our inspiration for this work was a 2024 thesis by PhD Thomas Roberts at MIT. The novelty of his work was that he created a method for determining if satellites were compliant based on only publicly available data, which had never been done before. And So we took inspiration from this by studying his program, deciding we were going to write our own Python program that was tailored to the needs of our project based on similar definitions of compliance. And the reason we did this is because we wanted to expand our experience in Python and also create something that would specifically show us distributions of countries that we could easily reproduce and share.
Yep, so ITU compliance basically assigns a specific compliance zone to different satellites as network allocations. So if a satellite is within that zone, then they are compliant. If they're outside of an assigned zone, then they're in non-compliant. So specific satellite longitudinal information is easily accessible and available to the public, as well as the ITU network assignments, which are publicly disclosed. The problem is the specific satellite network pairs are not openly available. So you don't know which satellite is supposed to be in which zone. So here we created a program that sort of matches different satellites and the specific zones that they could be a part of in order to determine whether they might be compliant or not. So here our program provides an end-to-end solution for determining satellite compliance. So we have an input user interface where you can determine like specifically by satellite, by country and whatnot. Then we have a data curation method, which sort of brings in information from different public sources. And then we insert this into a matching algorithm, which matches different satellite positions to their possible network compliant allocations. And then it results in statistical analysis, which we can do to see which country is the most compliant, least compliant, and other forms of information. So here's the methodology for overall matching algorithm pipeline. We take different signals, such as the daily satellite longitude, the brought to use launch date, and other pieces of information. We bring it into a matching system along with the registered ITU network band allocations, and we determine if the satellites are within 1 degree, 0.5 degree, 0.1 degree, or whatnot, based on the different signals that we input. So this creates a short list of possible network matches, which can be assigned to the specific satellite. So if there are no networks matched to the satellite, then the satellite has to be non-compliant because it's not legally allowed to be in that zone. And if there's more than one or more network matches, then the satellite is possibly compliant because it is allowed legally to be in that zone.
The graphs on this slide demonstrate the quantity of satellites deployed by each country, as well as the number of non-compliant satellites per country. As can be seen, the United States and People's Republic of China are the primary deployers of satellites by a significant margin, as they are two of the first countries to become involved with spacecraft. The data indicates that countries with longer space programs are more likely to be non-compliant, as they are more comfortable and familiar with the systems. There was also a difference between the non-compliant numbers from countries and from international organizations. The EUTE and SES were noticeably more compliant than the Commonwealth of Independent States and Canada, both of which had less deployed satellites. The countries with more established space programs may also have higher non-compliance due to increased power within the space system. This would explain why many important members of space programs, such as the US, People's Republic of China, and Canada, have larger numbers and percentages of non-compliance. In this graph, Angola and Bermuda are the most non-compliant countries, followed far behind by Canada. However, both Angola and Bermuda have only 1 to 2 satellites deployed, meaning that these numbers are actually deceptive. The right graph shows more useful data, as the United States and People's Republic of China combined consist of over 50% of all non-compliant satellites, with most small outliers like Angola or Bermuda consisting of a very small number of satellites, all of which were non-compliant.
In the graph to the left, it can be seen that both compliant and non-compliant satellite launches are gradually increasing at a steady rate. After a noticeable increase in 2000, the number of compliant satellite launches is very high, with non-compliant launches being relatively rare. This is important to consider, as it seems that despite some countries having very high non-compliance rates, most satellites remain compliant, a trend which seems to be improving. This graph displays satellite locations across a longitudinal spectrum, with some regions holding dominance where larger and more established countries are. The United States, for example, is represented in light blue and is dominating over the Western Hemisphere. In the Eastern Hemisphere, China and Russia dominate in the colors light, dark gray, and lime. Overall, it seems that countries with stronger space programs have less compliance, with some outliers where a few non-compliant spacecraft are the majority of a small number of satellites.
Altogether, we found that larger space programs like the US and China had the highest numbers of non-compliant satellites, whereas newer space programs like Angola and Bermuda had the highest percentages of non-compliance. This issue ultimately threatens key networks of weather monitoring, communications, the internet, and more. Our research can guide future action to ensure compliance for large and small space programs alike so that we can keep these critical GEO satellites safe. And since non-compliance both sources from and affects various countries, our findings highlight the need for international cooperation on such solutions. Moving forward, various space agencies must collaborate on international guidelines and agree to enforce IT regulations at the national level, such as through fines and licensing regulations. Additionally, we must simplify current global frameworks, as the ITU identifies overly complex regulations as a major barrier to compliance. We can also implement a novel reward/penalty system to incentivize improvement by limiting the abilities of non-compliant nations to launch new satellite missions or access shared resources like the Deep Space Network. And finally, future policymakers can aid newer developing space programs in improving their compliance rates, such as through assistance in drafting national regulations and through capacity building efforts like the satellite regulatory workshops. In the future, we can expand the scope of our compliance analysis to electromagnetic spectrum bands to check for stray signals. We can also survey space agencies and individual satellite operators about the challenges they face in following IT regulations. Furthermore, we can analyze how causal factors like national policies or access to technology can affect different countries' compliance rates. And finally, we can quantify the relationship between non-compliance and the risk for debris accumulation, space traffic, collisions, and signal interference.
These are our references. And we'd like to give a special thanks to our project mentor, Ms. Cara, as well as Ms. Baggio and Ms. Miller, the coordinators of the SEAS program. Thank you for all your guidance and for organizing this program. And thank you also for everyone else watching at home. We had a great time doing this project and we're glad we were able to share it with you.
So I would like for all members of the orbital debris team to please turn on their cameras and unmute their microphones. The first question for your team is there a reason so many non-compliant satellites to be launching? Okay, so I'm going to ask those of you who have mics on, turn them off. Let's see if we can stop the noise and try again. Oh, there we go. So I think we'll leave your mics off and let you join when you're going to answer the question. So the first question for the team is there a reason so many non-compliant satellites would be launching?
Yeah, sure. So I can take this question. So a lot of the time it can possibly be that satellites become non-compliant after a certain period of time. This could be such as they launch with the intent to stay in a specific zone and they sort of trend away over time as they involve different astronomical interference.
Has working on this project changed or encouraged your direction for your future career?
Yeah, I can take this one. So for me particularly, I was kind of on the fence of the aerospace industry. I wanted to study aerospace, but I wasn't sure if I wanted to study the aeronautical side, like jets and planes, or the astronautical side, which is satellites and rockets. But this project has helped me kind of lean towards the astronautical side because of our work with satellites. So yeah, definitely.
So I'm curious, did any of you really know much about orbital debris prior to this project? No, not really.
Definitely not.
What were ways used to check for astray signals?
I'll also take this one. So our project was only limited to the position compliance, which is basically where are the satellites in the sky and are they allowed to be there? The other half of compliance is electromagnetic signals, but we didn't have enough time to go into that because that is more complicated than position compliance. So that's why we suggested to expand upon our research in that field. So we don't know yet.
So the next question is, what do you think is the biggest threat due to non-compliant satellites?
I could take this one. The main threat with non-compliance is that, or I guess what's important to understand is that we need compliance to ensure that satellites stay within areas that they can safely remain in. So if satellites are non-compliant, that increases the risk that they could have collisions or that they could they could collide with, for example, other satellites or with orbital debris, which could damage the satellite to the point of even not being able to function anymore.
What future jobs in industry, technologies, and regulations do you see developing from the results found in your data on non-compliant satellites or spacecraft?
So for jobs, we could definitely have a sort of task force in NASA or different space agencies to sort of keep track of the non-compliance levels, such that if a certain network of their satellites are getting off course or different components of the systems are not aligned and not compliant over time, we can have that sort of task force within the space agencies in order to keep track of that, and also an external task force along with the ITU, which is working with the UN to sort of keep these space agencies in check.
Great work. Very interesting topic and an interesting project. Our next C's presentation is from the Proton temperature team led by Murthy Nauth, a PhD candidate at UC Berkeley, where she studies the plasma interaction in regions on Mars as part of the MAVEN mission.
Hello! We are the Proton Temperatures team, and over these past 2 weeks, we have been working with the NASA SEA's high school internship program to compare various qualities of protons in the time before, during, and after coronal mass ejections using satellite data from Earth and Mars.
Hey, I'm Jack Frangus, a rising senior going over there high school. I live in Atlanta, Georgia.
Hi, my name is Varun Rodricks. I'm a rising senior at Medina High School in Ohio.
Hi, my name is Alanis Marie Sierra Colon. I'm 17 years old and I'm from Puerto Rico, Vega Alta. I study in a school specialized in science and mathematics called Brigida Alvarez Rodriguez.
Hi, my name is Hital Benwani. I'm a rising senior at Centennial High School, and I live in Frisco, Texas.
Hi, my name is Shvika, and I'm a rising senior from the suburbs of Philly.
And our mentor for this project is Miss Murthy Nath, a PhD candidate at UC Berkeley who also works at the Space Sciences Lab.
CMEs are powerful solar eruptions that release vast amounts of plasma and magnetic fields from the sun's corona into space. Originating from areas of intense magnetic activity, such as sunspots, CMEs eject billions of tons of charged particles, traveling at speeds between 250 and 3,000 kilometers per second. When these particles reach Earth, they can cause geomagnetic storms, leading to intensified auroras, disruptions in satellite communications, and potential risks to astronauts. They occur with varying frequency depending on the solar cycle. During solar maximum, which is a peak of the approximately 11-year solar cycle, CMEs are more frequent and intense. And at this time, solar activity, including sunspots and flares, is at its highest, leading to a greater number of CMEs. This is the opposite when the solar minimum occurs. CMEs might occur less frequently, possibly only a few times a month. The aurora borealis, or northern lights, is a stunning natural light display seen in high-latitude regions around the Arctic Circle. This phenomenon occurs when charged particles from the sun, known as solar wind, interact with the Earth's magnetic field and atmosphere. As these particles collide with gases such as oxygen and nitrogen in the atmosphere, they create shimmering lights in various colors, including green, pink, red, and violet. This normally occurs in high-latitude regions near the Arctic Circle, including parts of Norway, Sweden, Finland, Canada, and Alaska, and they're most visible during winter months. The auroras are also more active during periods of high solar activity, which follows an approximately 11-year solar cycle. This is different on Mars. Aurora on Mars happens when charged particles from the sun, mainly solar wind, interact with Mars's localized magnetic field and atmospheric gases like carbon dioxide, producing that glow of ultraviolet colors. Unlike Earth, Mars lacks a global magnetic field, but its regional magnetic fields can trigger auroras, especially in southern hemisphere's volcanic regions. Martian auroras are more likely to are more likely during periods of high solar activity following an 11-year solar cycle. Although they're less vivid than Earth's aurora borealis, they can be best seen at night under clear skies.
Our goals for this project were to identify signatures for a previously studied CME, but using different Institute Earth data, and use those markers to see if we could identify unstudied CMEs, and to quantitate how fundamental property of the solar wind change your CME at Earth compared to a CME at Mars. By studying this difference in how CMEs impact both planets, we can count to understand not only the history of Mars and how its goal were to this today, but also how to protect astronauts aiming to set foot at Red Planet. We acknowledge the Community Coordinated Modeling Center, CCMC, at Goddard Space Flight Center for the use of GOES, DCGOV-R, and H data. We received the Mars data from Maven CY as well as GHelicast. The citation for all data will be included at the end of the slideshow. In the process, we graphed the line graph of 2018 Earth and Mars data to identify the patterns between before, during, and after CME hit. Use this pattern to figure out when 2021 CME began and ended. Do data from both CMEs and main histogram of each piece of data, density, temperature, etc., before, during, and after CME, to observe how the probability distribution for each piece of data changes in different stages of CME.
Starting with the 2018 Earth CME data, we observed that the density rises above pre-CME levels during the first CME and continues to increase into the second CME with a significant spike towards the end. The speed starts decreasing before the CME and continues to do so into the first CME before increasing about halfway through. During the second CME, the speed begins at a much higher level, decreasing initially and then rising again into the high-speed winds that follow the CME. The temperature during both CMEs appears much less sporadic compared to the pre-CME temperatures, with a notable bulge in the second CME. Let's move quickly to SIRs, or slow-fast stream interaction regions. SIRs occur when a faster solar wind overtakes a slower one, causing a disturbance. Our data and literature suggest that the patterns we expect during the second CME at Mars align more closely with those of an SIR. Similar to Earth, the density during the first CME at Mars is greater than the pre-CME density. However, in the second CME or SIR region, we see massive spikes in density. We also observe a steady decrease in speed before the first CME, a slight increase during the first CME, and a large increase in speed during the second CME. The temperature flattens out during the first CME with a notable peak, followed by two distinct regions in the second CME, one at a lower temperature and one at a higher temperature. Looking at the histograms representing this data, let's focus on the temperature column. The mode temperature of both CMEs at Mars is higher than the mode CME temperature at Earth. Both distributions display bimodal behavior during the second CME, which can be explained by the rise in temperature observed towards the end of the second CME.
For the 2021 Earth CME, we looked at data from the Discover, GOES, and ACE satellites. One of the most prominent features was an increase in proton flux values by an order of magnitude. Additionally, the Kp index from the NOAA spiked to values over 9. As for the CME at Mars, we were able to look at proton temperature, speed, and density from the Martian Maven satellite. The most significant feature was a clear spike in proton temperatures, along with a general increase in density and velocity values during the CME. Graphing the 2021 Earth CME data as histograms revealed more interesting trends. Temperature decreased by an average factor of 4 during the CME, then held a bimodal distribution for the rest of the CME, beginning to degrade post-CME. This is in line with what happened at Earth in 2018, albeit a bit weaker of an effect. In addition, velocity histograms revealed another bimodal split in the velocities, which had a peak increase of 300 kilometers per second during the CME then post-CME underwent a 150 kilometer per second increase in ambient solar wind speeds, which is what we believe resulted in the aforementioned split. Looking at Mars data plotted as histograms, we were able to see, similar to previous trends, proton temperatures saw a marked decrease in response to the initial CME shock. However, unlike previous instances, proton temperatures didn't assume as obvious of a bimodal distribution as they had in previous post-CME observations. Solar wind velocities saw little increase during the CME at Mars. However, post-CME, there was a significant increase of around 150 kilometers per second, similar to what happened post-CME at Earth in 2021. Lastly, there was a significant increase in proton density, going from an average of 1 per cubic centimeter to 10 per cubic centimeter during the CME, which resulted in a split. However, a similar effect was not observed at Earth in any previous observations. Comparing the 2021 versus 2028 CME effects, the 2021 CME had significantly more noticeable effect on proton flux at Earth than the 2018 CMEs. Additionally, proton temperatures at Earth in response to the CME seem to be bimodal in their distribution, and this trend was seen at Mars during the SIR, but not at CME, neither in 2018 nor the 2021 CMEs. Proton density enhancements were similar at both planets in response to the 2021 CME, about an order of magnitude enhancement from 1 per cubic centimeter to 10. And lastly, at Earth, the solar wind velocity distribution was isotropic and spread out across 200 to 600 kilometers per second, compared to Mars, which showed a bimodal distribution with peaks at 350 kilometers per second and 500 kilometers per second.
So, to summarize our results, we found that the 2021 CME has a bigger impact on both Earth and Mars because we could identify direct responses to the CME in our time series data. We're also seeing that a bimodal temperature distribution was observed at Mars after the SIR, stream interaction region, that brushed Mars in 2018, but that wasn't the case for any of the CMEs that impacted Mars, which we studied. Overall, the proton densities changed similarly on both planets in response to a CME, but proton temperatures and proton velocities were impacted very differently on the two planets. So in conclusion, from what we've found, the way that energy is exchanged by the Sun and its planets is different when the Sun interacts with Earth versus when it interacts with Mars. This is proved by the fact that, in response to the same CME, both Earth and Mars experience similar enhancements in proton densities, but different effects on the velocity and temperature of the solar wind. Both of these values were lower at Mars than at Earth. Additionally, the bimodal distribution of proton temperatures at Earth as a response to the CME should be further investigated. CMEs ejected from the Sun cool differently than how the ambient solar wind cools, and we don't know why. More studies would help us understand why this happens. And finally, we need continuous space weather monitors at Mars if we want to send people there one day, even when the Sun is in solar minimum. This is when SIRs are more likely. Because the many differences between the atmospheres and magnetic fields of Earth and Mars, which will impact how energy and momentum are exchanged between each planet and the Sun, make it hard to predict how various factors like CMEs will impact Mars and consequently any people living there. So, you cannot rob me of free nature's grace. You cannot shut the windows of the sky, through which the aurora shows her brightening face. This excerpt is from the 18th century, and yet it still holds true today. We can't stop auroras or the CMEs that cause them. All we can do is keep learning about them so that one day we can traverse them without fear. We all had an amazing time during our SEAS internship. Some of the best parts were getting experience in research utilizing real satellite data, meeting other students interested in Earth and space science, listening to talks from so many people who already work in this field, working with an amazing mentor, and learning so many new things. Every day in this internship was a new adventure. However, we did face several challenges, including our time management with so much data to analyze, our asynchronous communication across time zones as a virtual group, and having to learn a lot about Python in order to write the code that would graph our data.
Yeah, I think SEAS has really been a beneficial experience in that it's taught me what it's like to do kind of like real research, which I hadn't really had the chance to do before. It's taught me to work with other like-minded people. It's taught me how to analyze data and, overcome challenges. I think it's been a really useful experience for everyone in my group.
I think my favorite part of working in the C's team was learning Python with everyone else, especially in the real application as opposed to the modules, because they were a lot different and it was a really fun challenge to overcome.
This virtual internship helped me to know where I want to direct my studies and where I need to acquire more knowledge. Learning such an amazing fact about Mars helped me to understand the difference between Mars and Earth. But also, the most important thing, it led me to experience working with brilliant Mars, like my team members and mentors.
Okay, so maybe this is a cliche, but I've been fascinated with space for as long as I can remember. I used to spend hours watching brain pop videos about black holes and exoplanets and any other space topic that I could find. The NASA SEAS program has really helped me reignite that interest and pushed it further than I ever could have imagined. This program has inspired me to want to keep learning about space in some capacity long into the future.
I developed an interest in space from an early age when I used to read astronomy books with my dad. From the closest planets to the furthest galaxies, I read about everything in between, including black holes, dark matter, nebula, and more. Unfortunately, I'm far from knowing everything about space, which is why I love it so much. There is so much we have yet to learn, and when I grow up, I hope to be a part of those discoveries. The best part about this internship was learning something completely new. It never occurred to me that CMEs would significantly affect Earth and even Mars, so it was really interesting analyzing all that data. SEAS has inspired me to consider pursuing a career at NASA working in Earth science or space. It's equipped me with the necessary skills to succeed in college and beyond.
Thank you, everyone, for listening to our presentation. On behalf of all of us, a huge thank you to all of the SEAS staff and mentors, especially Miss Miller, Miss Baguo, and especially our team mentor, Miss Noth. We literally could not have done it without you.
So I invite all the proton temperature team to turn on their cameras. We'll do one microphone at a time as you're answering the question for bandwidth. So based on your studies, can we predict CMEs on Earth?
I guess I'll take this question. I think that currently there are already instruments orbiting the sun that you can use to predict CMEs. And as we mentioned, it takes at least 15 to 18 hours for them to get here. So I think currently we can sort of predict them. Our research is more focused on applications of how they might impact space travel. But I think potentially if we notice some spikes in the data before the CME hits, then potentially, but I think we can already do that at this point.
So the next question follows on with your answer. So does someone on the team want to answer, how will CMEs affect plans for space travel to Mars and beyond?
I think I can take this one. So something that we kind of learned from our analysis is that CMEs affect Earth and Mars in very different ways. Even though, relatively speaking, they're, neighbors, CMEs still affect them in different ways. So in order for us to understand the full effects that CMEs would have on space travel, one of the key takeaways we saw is that more research needs to be put into finding out how CMEs affect Mars. In order to do that, we need to have more advanced equipment to take better measurements and a wider range of measurements at Mars and in between.
It was interesting that the temperature would decrease during a CME. What was the reasoning for that?
Sorry, I'll take this. So we don't know exactly why yet that the temperatures decreases, but we do know it's a consistent effect of the initial shocks that are carried by CMEs.
That has been seen in previous studies, and it's the typical signifier of an oncoming CME.
And then our last question for this team, would humans experience the same changes that are identified by the changes in proton temperature? And they loved your quote.
I guess I'll take this one. Thank you. I love that quote too. And for the humans experiencing the same changes, we do know that CMEs, like the reason that they're so significant is because, like I said, they take out satellite communication, they take out, I believe that humans at like the International Space Station have to like take shelter. So CMEs can have huge radiation impacts on humans. And so the proton temperatures, they do like Jack said, we do have a consistent pattern that tells us that something is happening during a CME. But then I don't think so far, like I don't know about what the human impacts would be like. We know that things are significantly changing in the atmosphere during a CME, but we don't exactly know how or why that's going to impact humans. And quite honestly, we do not want to find out.
Well, you did a great job in your research. It was very interesting. So please welcome the Artemis Geology team, led by mentor Suzanne Foxworth, a contractor at Jacobs Technology in the Astromaterials Research and Exploration Science Division at NASA Johnson Space Center. Suzanne manages the Lunar and Meteorite Sample Disk Program, and Maritza Montoya, who is a small particle processor at Jacobs, supporting the Hayabusa 2 and OSIRIS-REx missions. Please welcome Team 1 of the Artemis Geology Prototype Tools for NASA Return Mission team.
Hi. This is our presentation on the Artemis Geology Prototype Tools for NASA Return Missions. This project was done by Team 1 of the NASA SEAS VGE team, which is Raghav Alialamangalam, Sahash Bhargava, Ayan Chawla, and Kunal Shah.
Our project focuses on designing a prototype tool and container for lunar sample handling. We utilize CAD software for design and prototype creation. In preparation, we research past NASA missions and existing tool and container designs. Training involves learning CAD software to create precise 3D models, while collaboration with team members allowed for the integration of these diverse design ideas. Our goals were to master AutoCAD and Fusion 360 to quickly produce STL files for 3D printing, and ensure the tools and containers are reliable and, most importantly, contamination-free through improvements based on regular feedback and testing.
As per methods, our group researched various types of containers until we identified vacuum-sealed cylinders as the optimal choice for our project. We determined that these containers would be the best due to their ability to preserve sample integrity by preventing contamination and outgassing. Additionally, their efficient space utilization, inherent in their cylindrical shape, made them particularly well suited for the constrained environments of space missions. Each member of our team designed their own vacuum-sealed cylinder prototypes, allowing us to incorporate a variety of perspectives and ideas into the final design. This collaborative approach ensured that our final prototype was versatile, integrating the best features from each individual design. Initially, some of us proposed an O-ring design to achieve a vacuum seal, while others suggested using threads. Both approaches had their merits. The O-ring design offered a simple and reliable seal, while the threaded design provided additional security and ease of use. After further evaluation, we decided to combine these two methods. Our final prototype features a hybrid design that utilizes both O-rings and threaded components, offering enhanced sealing capabilities and structural integrity. Furthermore, we drew inspiration from our original wrench tool design, which was intended to facilitate sample collection and handling. We adapted this design to create a specialized tool that works seamlessly with our new cylindrical containers. This tool ensures that samples can be collected, sealed, and transported with minimal risk of contamination or damage.
We found that our prototype was best with both an O-ring and threads to create a vacuum-sealed container. And we also found that after 3D printing, our tool did open up our container, which means that we were successful. Our container could be used on the Artemis space mission to collect about 225 grams of lunar regolith samples, which also exceeds the 10-gram initial requirement that we were given at the beginning of our program. Our container is also lightweight and efficient enough to be a feasible addition to the Artemis mission. And some future possibilities for our container include that one change could be changing the material of the container and tool to be made of anodized aluminum because of its durability and low density. And another area of improvement could be to create a rounder lid to reduce the chances of glove tears and contamination of materials. This video shows a demonstration of our tool being used to open the container we built. The half hexagonal shaped tool is being used to open the container by rotating the hexagonal lid. After opening up the lid using the hexagonal tool, the cylindrical rod end of the tool is being used to open up the container. This video shows a quick time lapse of our container and tool being printed. On the left side, you can see the 3D models of the container, tool, and the container's lid that our team created. And on the right side, you can see the real-life 3D printed versions of our container, lid, and tool.
Acknowledgements. We would like to thank Margaret Baglio, Salima Miller, Maritza Montoya, and Suzanne Foxworth, all of the NASA Aries speakers, all of the SEA speakers, and the University of Texas Center for Space Research for helping us with this project.
Our team has greatly benefited from the SEEDS program, which has significantly enhanced our understanding of 3D design and engineering applications. We gain invaluable hands-on experience with CAD software and engage in NASA project simulations, offering us unique insights into the real-world challenges of space missions. Among the best features of the program, we appreciated the exposure to advanced technology and tools, the opportunity to work on impactful projects related to space exploration, and the collaboration with experienced mentors and peers. However, we faced challenges such as adapting to various CAD software and file formats, coordinating team efforts across different design components, and meeting tight deadlines while maintaining high-quality outputs. Overall, the SEEDS program has provided us with essential skills and experiences that will guide our future endeavors.
Here are some reflections from members of our group. SEAS helped me learn more about 3D design and moon missions, which were fields I would not have explored without this program. SEAS has also helped solidify my interest in geology, and I plan to study it in college and beyond. SEAS has had me learn a lot more about and practice 3D modeling and design, which was really helpful and interesting. Learning about the requirements and restrictions for tools and containers that would be used in NASA missions was really interesting and reinforced my intention to study design in college. The SEAS program has deepened my interest in engineering by providing hands-on experience with 3D design and NASA project simulations. This exposure has clarified my goal to pursue a career in engineering, where I hope to contribute to innovative projects in the future. Here is our poster that we created for this project. Similarly to our presentation, our poster has sections for the abstract, background, materials and methods, results, conclusions, and acknowledgements. Thank you for your time.
So please join me in welcoming the next Artemis Geology Prototype Tools for NASA Return team.
Hi everyone, we are Team 2 from the Artemis Geology and Prototype Tools for NASA Return Missions team, and our members include Devane Palaniappan, Bobby Bress, and Allison Huang. Our project focuses on designing and prototyping a tool and container to securely transport and handle lunar samples for the Artemis missions.
So, our main objective was to design a container that will transport lunar samples back to Earth. These lunar samples include rocks, regolith, dirt from the moon, and it has to be all contained so that it can go back to Earth. And also, we had to design a tool that could open and close this container to make sure that these samples would not become contaminated and they could be safely transported back to Earth. In preparation for these, we first completed Earth science modules which NASA provided us. This included videos with quizzes and slideshows we had to make so that we could learn a lot about NASA's work so that we could be more effective interns. We learned to use 3D designing softwares. These included Front Panel Designer, Tinkercad, and Fusion 360. All of these helped immensely in helping us accomplish our task. And we also had to review the Apollo Tools Catalog. This was a catalog made in the 60s and 70s when NASA was going to the moon through their Apollo missions, where it outlines all the containers and tools they used in order to collect and contain the moon samples so that they could be effectively brought back to Earth. This helped give us ideas for what we wanted to do and helped inspire our design. Our goals for this project was to collaborate effectively with our team online, as especially for 3D designing, it isn't easy when you're not in the same room as each other, so we had to figure out how to do that effectively. We need to learn to use 3D design software, the ones that we listed above. We had to understand lunar sample handling so we could more effectively contain the lunar samples so that they would not become contaminated and could be brought back to Earth.
To make our prototype, we began with a rough sketch of our design, focusing on the essential features needed to safely hold and transport the lunar samples. From this initial sketch and preliminary dimensions, we used calculations shown on the right to estimate the dimensions of the container. We utilized the density formula and kept in mind that the density of most lunar regolith is about 1.5 grams per centimeters cubed. Ensuring that our design could hold up to 10 grams of lunar regolith was a key requirement of our project. The density and abrasive nature of lunar regolith were also carefully considered during this phase to ensure the container's durability and capacity. Next, we moved on to 3D prototyping, utilizing Autodesk Fusion 360 for several critical elements of the design. We created a hinge and latch system to ensure that the box could be securely opened and closed. The hinge system was modeled to withstand the harsh conditions of lunar transport. Additionally, we created a joint modeling system in Fusion 360 to test the box's structural integrity and functionality. To further refine the opening and closing mechanism, we used Tinkercad to integrate the tool design and the rings seen on the lid to facilitate easy access while maintaining the sealing. This involved creating a precise and user-friendly mechanism that allows for the safe and efficient retrieval of the samples. Our container is designed to hold a maximum of 10 grams of lunar sample, considering the sample's weight and the need for secure containment. We kept in mind the fact that the container should provide an airtight seal to prevent any contamination and preserve the lunar samples for future scientific analysis. This airtight sealing is critical to prevent exposure to the Earth's atmosphere, which could alter the sample's properties.
Okay, as for the results, our design did work as intended, but it could be modified for ease of use. The hinge was slightly too large and didn't fit from the lid to the container. Our future plan is to optimize the container dimensions to ensure a perfect fit with the lid. The hole that we used to open the container didn't fit correctly, and in the future we may reprint it with a stronger filament material. We'll also resize the hole and the thickness of the tool used to open the container so that it's better supported. And more of our future steps, we will finalize the container and tool design for a perfect fit, and we will reduce unnecessary space to make the container airtight. As for choosing the material used for the box, NASA uses 3 main materials: stainless steel, anodized aluminum, and Teflon. And we decided to choose anodized aluminum to reinforce the box's structural integrity.
Here we have a variety of images of our design and our product. In the top left, that is a design that we made in Fusion 360 that shows the dimensions and from a variety of different angles. Below it, you can see a design of the tool also from Fusion 360. And to the right of that, you can see the box in Tinkercad where the lid is attached. But upon printing, the lid and the container are printed separately, as the lid is meant to attach through the hinges onto the container. Our first attempt, as you can see with the green box in the bottom left of the right, the hinge didn't exactly fit in right, and we believe this was an error in the printing, as we used a different printer, and on the black box, as you can see on the top right picture, it fit much better onto the container. Through the black box, you can also see the hook tool, which on the bottom right shows how the hook can go into the hole to open and close the container to make it so that it can transport the lunar samples.
We'd like to thank the following people for this amazing opportunity. We'd like to thank Margaret Baggio and Selena Miller for making this all possible. We'd also like to thank our mentors, Maritza Montoya and Suzanne Foxworth, for their invaluable guidance and assistance throughout this whole process. Finally, we're grateful to all the NASA Ares speakers, the SEAS speakers, and the University of Texas Center for Space Research for giving us this incredible opportunity to contribute to the Artemis missions.
Some of the highlights for this program: the SEAS program has allowed us to learn how to work collaboratively in a scientific setting, and one of the best features of this internship was the guest speaker sessions. We really enjoyed hearing from industry experts and NASA engineers who shared their experiences and expertise. One of our biggest challenges that we had to face was communicating effectively online. The 3D design software we used wasn't collaborative, so it was difficult to adapt our designs. I'm Allison, and I gained a better understanding of what NASA engineers do and the skill sets needed in the field. I've also become more interested in pursuing a career in aerospace engineering.
My name is Devane, and my SEAS experience has enhanced my interest in STEM. It's motivated me to pursue a degree in aerospace engineering with the goal of contributing to future space exploration missions.
I'm Bobby, and SEAS has shown me a lot about how NASA runs and has taught me a great amount about different parts of the industry. Here you can see our poster where we go over a variety of what we've already gone over in the slideshow, like the abstract, the methodology, conclusion, etc. And as you can see on the right, there's more images, some of which we have shown, some of which we haven't, that show our design and our product.
Thank you.
So we invite all team members from the Artemis Tools Project to please turn on their cameras. And when you are ready to answer a question, if you would, please unmute your mic. So the first question is for team number 1. Was the 3D printer already owned by someone on your team or something you had to get for this project? Was it hard to use because of the virtual format?
I can answer that question. So personally, like I owned a 3D printer before this program, but we also had access to a 3D printer through our mentors, and working on this project. Like using a 3D printer for this project was not really difficult because we could just email each other the files that were needed to be printed or modified before we finalized our prints.
Great, good teamwork. Can you discuss one or two of the constraints in designing geologic tools to be used outside of Earth? This is also for Team 1.
Yeah, so one of the main constraints that we looked to work on was minimizing the amount of sharp corners and like edges on our tools and containers, because our mentors had told us that on space missions, sharp objects can potentially tear astronaut suits, which is something you don't want. So we try to minimize that in our design.
Great. Team number 2, how can your prototype be tested here on Earth to accurately simulate using the tool off of Earth?
Yeah, I can take that question. So after printing at the Johnson Space Center, our mentors used the tool as it would be used on the moon and for these space missions. So it's just the same straightforward, can it open and close, and how secure is it when it opens and closes? But other than that, there aren't that many factors that are considered.
And also for team 2, was lunar material a consideration in the design of your prototypes? If so, what part of your design reflects those considerations?
Well, one of the main aspects about lunar material we had to take into account was the weight, because we needed it to be a maximum holding of 10 grams of lunar material. So to calculate the dimensions of the container, we had to use the density of lunar dirt to estimate what the dimensions of our container should be.
Great. Well, you all did an excellent job. I learned a lot, and congratulations on your design. I know it's difficult working in a virtual environment with hands-on projects. The success of SEAS is determined not only by the commitment and research conducted by our student interns, but also by the mentors and our project assistants. To our NASA subject matter experts and project assistants, your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded and is certainly unmatched. Our special thanks to all SEAS mentors, your dedication to youth development and STEM education. I know the SEAS interns join me in thanking you for your dedication and commitment. A special thanks to the SEAS project assistants, project associates, and our CSR summer interns who assist in making the SEAS program a huge success. A special thanks to you and to the CSR administrative staff for their assistance. The whole SEAS education team joins me in thanking you for your time and your talent shared with our student interns. I know the SEAS interns appreciate your guidance and advice as they conducted their research. A special thank you to the NASA SEAS Earth System Explorer peer mentors who assisted that team in guiding their student research. And a special thanks to our communications coordinator, who is the one that keeps you all up to date on your social media, is posting your photographs, and put this whole slide presentation together for the last 2 days. It's a massive undertaking at the last minute when we're getting those presentations together. So thank you, Angelica. This concludes the NASA STEM Enhancement in Earth and Space Science Symposium for the 11th grade students. Thank you for watching these amazing students as they share the results of their internship and their research. The future certainly looks bright for these young engineers and scientists of